highlighting how even a slight shift in atmospheric or environmental conditions can lead to dramatically different outcomes. Studying Venus allows scientists to better understand the effects of a runaway greenhouse effect. This phenomenon occurs when a planet's atmosphere traps heat to such an extent that it leads to extreme surface temperatures, drastically altering the planet's environment and making it inhospitable. By examining the mechanisms at play on Venus, researchers can gain insights into how increased levels of greenhouse gases on Earth could impact our climate. This understanding is particularly relevant in the context of ongoing climate change and the continued rise of carbon dioxide and other greenhouse gases in Earth's atmosphere. Furthermore, Venus's geological features, such as vast plains of volcanic rock and other signs of past volcanic activity, suggest that its surface has undergone considerable change over time. Understanding the geological history of Venus can provide clues about planetary evolution and the potential for catastrophic geological events, which in turn could inform our knowledge about the stability of Earth's geology. The study of Venus serves as a reminder of the delicate balance that sustains life on Earth. By learning from the extreme conditions on our neighboring planet, scientists can develop models to predict how human-induced changes might influence Earth's climate and environments in the future. This knowledge reinforces the importance of environmental stewardship and highlights the need for action to mitigate the risks associated with climate change, ensuring that our planet remains a suitable haven for life. The vast storms on gas giants like Jupiter and Saturn are fascinating phenomena that arise from their unique atmospheric conditions and immense sizes. The primary driver of these storms is the complex interplay of heat, rotation, and atmospheric composition. Jupiter, for instance, emits more heat than it receives from the Sun due to residual heat from its formation and ongoing gravitational compression. This excess heat fuels powerful convection currents which rise and create vast storm systems. The swirling patterns visible in Jupiter's atmosphere, such as the Great Red Spot, are essentially enormous cyclonic storms that have persisted for centuries, driven by these dynamic processes. Saturn exhibits similar storm formation, although its storms can be even more dramatic due to the planet's strong winds and very low temperatures at higher altitudes. One of the remarkable features of Saturn is its hexagonal storm structure at the North Pole, a phenomenon that scientists continue to study. The unique geometry of this storm is likely influenced by the planet's rapid rotation, which can affect airflow patterns and create the sharp edges observed in the hexagon. Both gas giants are characterized by high wind speeds, with storms that can reach hundreds of miles per hour. The persistence of these storms is also attributed to the gas giants' thick atmospheres, composed primarily of hydrogen, helium, and other trace gases that provide the fuel for ongoing storm activity. Unlike Earth, where storms are often short-lived and influenced by land masses and water bodies, storms on Jupiter and Saturn can last for extended periods due to the lack of such factors. The continuous input of thermal energy and the immense scale of these planets allow for the maintenance and evolution of their storm systems over long time frames. Intriguingly, the study of these giant storms goes beyond mere curiosity. It aids our understanding of atmospheric dynamics on other planets. By investigating the storms on Jupiter and Saturn, scientists can glean insights that apply to weather systems on Earth and even extrapolate findings to exoplanets, deepening our knowledge of atmospheric phenomena across the universe. Evidence suggesting the existence of Planet 9, a hypothetical planet beyond Neptune, primarily stems from the unusual orbits of several distant celestial objects in the Kuiper Belt. Researchers have observed that numerous trans-Neptunian objects, TNOs, exhibit strange clustering in their orbits, deviating from what would be expected based solely on the gravitational influences of known planets. This clustering suggests a gravitational force from an unseen massive object, leading scientists to propose the existence of a yet undetected ninth planet. One of the key pieces of evidence is the orbits of these distant TNOs, which have highly elongated and tilted trajectories. Many of these orbits appear to align in a way that suggests they are being shepherded by the gravity of a large planet far beyond Neptune. The theoretical Planet 9 is expected to have a mass estimated to be between 5 and 10 times that of Earth, and to orbit the Sun at an average distance significantly greater than that of Neptune, possibly taking thousands of years to complete one orbit. Additional support for the Planet 9 hypothesis has come from simulations that model the gravitational interactions between the known objects in the Kuiper Belt and a hypothetical Planet 9. These simulations indicate that a massive body could dynamically stabilize the orbits of the TNOs observed, thus aligning with the unusual patterns seen. Some researchers have also noted that certain scattered disk objects, which are more distantly situated, might be influenced by the gravity of a huge planet. While direct observational evidence of Planet 9 has yet to be found, the tantalizing clues from its potential gravitational effects create a compelling case for its existence. Ongoing efforts utilizing advanced telescopes and survey missions aim to search for this elusive planet in the hope of confirming its presence. Discovering Planet 9 would not only reshape our understanding of the solar system, but also provide insights into its formation and the mechanisms that govern the orbits of distant celestial bodies. Comets and asteroids serve as time capsules containing primordial materials from the early solar system, offering invaluable clues about its history and formation. These small celestial bodies are believed to be remnants from the solar system S formation, preserved in relatively unchanged states since their creation roughly 6 billion years ago. By studying their composition, scientists can gather information about the conditions present in the early solar system and the processes that shape the planets. Asteroids, primarily found in the asteroid belt between Mars and Jupiter, are rocky remnants that have not undergone significant alteration. Their mineral content and isotopic ratios provide insight into the building blocks of planets and the early solar system SS environment. For example, certain types of asteroids contain clay minerals, which suggest that liquid water may have played a role in their formation, indicating that water was more abundant in the early solar system than previously thought. Comets, on the other hand, are composed primarily of ice and dust and originate from the outer solar system, such as the Kuiper Belt and the Oort cloud. When comets approach the Sun, they develop tails due to the sublimation of their icy components. The study of cometary materials can reveal organic compounds and various volatile substances that existed in the primordial solar nebula. This information points to the potential for complex chemistry that could have led to the emergence of life on Earth. The identification of specific compounds, such as amino acids in some comets, reinforces the hypothesis that these icy bodies may have delivered organic material to our planet. Exploration missions to examine comets and asteroids have yielded exciting findings. For instance, missions like NASA's OSIRIS-REx, which visited the asteroid Bennu, and the European Space Agency s-Rosetta, which orbited Comet 67P Churyumov-Gerasimenko, have provided detailed data on their surfaces and compositions. These missions have confirmed that the materials found in these small bodies are crucial for understanding how the solar system formed and evolved. The presence of different types of asteroids and comets, each with unique characteristics, further enriches our comprehension of the diversity of building blocks available in the early solar system and their roles in shaping planets. The Kuiper Belt and the Oort cloud are both essential regions of our solar system that provide critical insights into its formation, evolution, and the dynamics of celestial bodies beyond the planets. The Kuiper Belt, located just beyond Neptune's orbit, is populated with numerous small icy bodies, including dwarf planets like Pluto and Haumea. This region serves as a repository of primordial material that has remained relatively unchanged since the solar system S formation. Studying the Kuiper Belt allows astronomers to gain a better understanding of the composition, structure, and distribution of the building blocks that contributed to the development of the planets. One intriguing aspect of the Kuiper Belt is its influence on the gravitational interactions within the solar system. The presence of numerous trans-Neptunian objects can help scientists decipher the historical gravitational influences from planets like Neptune and how they shape the evolution of the solar system. The orbits of Kuiper Belt objects can also provide clues about the nature of planetary migration, helping us piece together the complex history of our cosmic neighborhood. The Oort cloud, on the other hand, is a hypothetical region believed to encompass the solar system, extending far beyond the Kuiper Belt. It is thought to contain a vast number of icy bodies and is the presumed source of long-period comets that enter the inner solar system. The existence of the Oort cloud is inferred from the behavior of these comets, which often originate from highly eccentric orbits that suggest they were perturbed from a distant spherical shell surrounding the solar system. Studying these comets can reveal information about the early solar system-esque conditions and the processes that shaped its evolution. Understanding both the Kuiper Belt and the Oort cloud is vital for comprehending the solar system's overall structure and the potential for dynamic interactions within it. These regions may hold remnants of the early solar system, offering valuable insights into planetary formation and the history of celestial bodies. They also pose important questions about the potential for life in distant solar systems, as the materials found in these regions may be similar to those that contribute to habitability elsewhere in the cosmos. Together, they form a key component of our quest to better understand not only our own solar system, but also the processes that govern planetary systems throughout the universe. The vast space between our solar system and the nearest star, Proxima Centauri, is known as interstellar space. This region is incredibly expansive and mostly empty, characterized by an incredibly low density of particles. On average, there are only a few hydrogen atoms and trace amounts of helium, as well as some heavier elements in a cubic centimeter of interstellar space. Despite its emptiness, interstellar space is not devoid of phenomena. It contains intriguing structures and materials that can provide insights into the nature of our galaxy. One significant component of interstellar space is the interstellar medium, which consists of gas and dust. This medium plays a crucial role in the formation of new stars and planetary systems. Regions with higher concentrations of gas and dust, known as molecular clouds, are the sites where gravity can overcome internal pressure, leading to the collapse of material and subsequent star formation. Observing these clouds can help astronomers understand the life cycle of stars and the processes involved in building new solar systems. Interstellar space also features cosmic rays, which are high-energy particles that travel at nearly the speed of light. These particles can originate from active solar events, supernovae, and other cosmic phenomena. Cosmic rays can have various effects on the solar system, from impacting satellite operations to influencing the evolution of life on Earth by altering atmospheric chemistry. Additionally, interstellar space is marked by magnetic fields that permeate the galaxy, helping to organize matter and influence star formation. These magnetic fields affect how gas and dust behave in this region and play a role in the movement and interactions of particles. The interplay of these magnetic fields with the solar wind, the continuous flow of charged particles from the sun, creates a complex environment that affects the boundaries of our solar system. Ultimately, while the space between our solar system and the nearest star may seem empty and desolate, it is filled with fascinating processes and materials that reveal a great deal about the universe. Studying these elements enhances our understanding of galactic dynamics, star formation, and the potential for life elsewhere in the cosmos. Interstellar dust and gas clouds, often referred to as molecular clouds, are essential to the processes that lead to the formation of new stars and planetary systems. These clouds consist primarily of hydrogen molecules, along with other gases and a mix of cosmic dust particles. When regions within these clouds undergo gravitational collapse, they create the conditions necessary for star formation. The process begins when a portion of a molecular cloud becomes dense enough, often due to shock waves from nearby stellar events like supernovae or the collision of two clouds. This increase in density results in regions that can no longer support their own weight against gravity, causing them to collapse. As the material falls inward, it forms a rotating, flattened disk of gas and dust that eventually leads to the birth of a new star at the center, while the remaining material in the disk can coalesce to form planets, moons, and asteroids. The presence of interstellar dust plays a crucial role in this process as well. Dust grains in these clouds can absorb and scatter light, helping to cool the surrounding gas. This cooling is vital as it facilitates the loss of thermal energy, allowing the gas to collapse further under its own gravity. Without dust, The gas would remain too warm to condense efficiently, slowing or preventing star formation altogether. Additionally, the chemical reactions that occur on dusty surfaces are fundamental to building the basic molecules required for planet formation. These reactions can produce complex organic molecules, which may eventually play a role in the emergence of life. When the dust and gas settle into a protoplanetary disk around the newly formed star, the solid material can begin to stick together, forming larger bodies through a process called accretion. Over time, these bodies can grow to become planets, moons, and other small solar system objects. The interplay of interstellar dust and gas clouds influences not only the formation of individual stars, but also the characteristics of the emerging solar systems. Factors like the density of the parent molecular cloud, the presence of other stars, and the surrounding environment can lead to a wide variety of star systems with different numbers of planets, diverse compositions, and varying distances from their host stars. The processes occurring within these interstellar clouds serve as the starting point for the complex tapestry of stars and planets that populate our galaxy. The significance of the Voyager probes crossing into interstellar space is profound, marking a historic milestone in human exploration and our understanding of the cosmos. Launched in 1977, Voyager 1 and Voyager 2 were initially designed to study the outer planets of our solar system. However, their journeys have extended far beyond their original missions, providing invaluable data about the environment of interstellar space and enhancing our knowledge of the solar system's boundaries. When Voyager 1 crossed the heliopause in 2013, it became the first human-made object to enter interstellar space. The heliopause is the outer edge of the solar wind's influence, where it meets the interstellar medium, the thin gas and dust that fills the space between stars. By traversing this boundary, Voyager 1 began collecting data about the properties of interstellar space, including the density and temperature of the interstellar medium, cosmic rays, and the magnetic fields found in this remote region. This information helps scientists understand the interactions between the solar wind and the surrounding interstellar environment, offering insights into fundamental astrophysical processes. Voyager 2 followed in 2018, also crossing into interstellar space, but through a different route, providing complementary data. Both probes are now traveling through a region of space never before explored, enriching our understanding of the broader galactic environment. Their findings contribute to our knowledge of how the solar system interacts with the galaxy, including the influence of the interstellar medium on the solar wind, the structure of the heliosphere, and the behavior of cosmic rays. The data collected by the Voyager probes continue to shape our understanding of the universe, providing a unique perspective on the outer reaches of our solar system and the vast, uncharted territories beyond. The Voyager missions have provided crucial insights into the structure and dynamics of the heliosphere. Additionally, the Voyager spacecraft carry the Golden Records, which contain sounds and images representing life on Earth, intended to communicate with any intelligent extraterrestrial beings that might encounter them in the distant future. This aspect of the mission highlights humanity's search for connection beyond our planet and serves as a cultural artifact for future generations. The Voyager probe's journey into interstellar space has advanced our scientific understanding of both our solar system and the galaxies beyond. Their continuous transmission of data symbolizes the spirit of depths of space, creating a bridge between our home planet and the vastness of the universe. Detecting and studying rogue planets, celestial bodies that drift alone through interstellar space without being bound to any star, presents a unique challenge for astronomers. These planets typically lack the bright light associated with stars, making them difficult to spot. However, advancements in technology and innovative techniques have allowed researchers to identify and study these elusive wanderers. One primary method for detecting rogue planets is through the observation of gravitational microlensing. This phenomenon occurs when a massive object passes in front of a more distant background star. The gravitational field of the rogue planet can bend and magnify the light from the distant star, leading to a temporary brightening that can be detected from Earth. By monitoring large patches of the sky and looking for these brief changes in brightness, astronomers can infer the presence of rogue planets. Another valuable technique involves infrared observation. Many rogue planets are believed to be cold and faint, emitting most of their energy in the infrared spectrum rather than visible light. Large ground-based telescopes and space observatories equipped with infrared detectors can capture the thermal emissions from these planets. By examining the infrared signatures, astronomers can gather information about their temperatures and potential atmospheric compositions, providing critical insight into their characteristics. Additionally, researchers often rely on data from surveys that track large numbers of stars and celestial bodies, such as the European Space Agency's Gaia mission. Gaia is mapping the positions and motions of billions of stars, and leveraging this data can help identify outliers that might indicate the presence of nearby rogue planets. As survey technology improves, astronomers continue to enhance their ability to detect these wandering planets. Although rogue planets do not have traditional stellar orbits, studying them can offer valuable insights into the formation and evolution of planetary systems. Their existence may challenge some theories of planet formation and migration, suggesting that a significant number of planets may be ejected from their home systems. Understanding these planets enhances our knowledge of the diversity of celestial bodies and the complex dynamics at play in our galaxy. As techniques improve and more discoveries are made, the study of rogue planets continues to shed light on the mysteries of the universe. Brown dwarfs are fascinating cosmic objects that help illuminate the gray area between stars and planets. These entities are sometimes referred to as failed stars, but their unique characteristics are what make them particularly valuable in understanding this boundary. Unlike typical stars that sustain hydrogen fusion in their cores, brown dwarfs are unable to ignite this process, instead exhibiting traits that resemble both stellar and planetary characteristics. These odd objects form in a similar fashion to stars. They arise from the gravitational collapse of gas and dust, just like their larger stellar counterparts. However, they lack the necessary mass to reach the core temperature and pressure needed for nuclear fusion to occur. A brown dwarf usually has a mass between about 13 times that of Jupiter and 80 times that of the Sun. This intermediate range places them in a unique position in the cosmic hierarchy, sparking discussions among scientists about the distinctions that define a star versus a planet. Observations of brown dwarfs reveal that they possess atmospheres with features akin to planets, including clouds and weather patterns. Their ability to capture and emit energy leads to a variety of temperatures and compositions, further blurring the lines between planetary and stellar classifications. By studying the light spectra emitted from these objects, astronomers can discern the chemical makeup of their atmospheres. This knowledge not only enhances our understanding of brown dwarfs, but also lends insight into the formation and evolution of both stars and planets in our universe. Understanding brown dwarfs helps refine our definitions and categories of celestial bodies. As researchers continue to study these enigmatic entities, they piece together hints about the processes that govern the birth and life cycles of stars and planets, challenging and expanding our existing knowledge of the cosmos. The continuing investigation into the intricate characteristics of brown dwarfs will undoubtedly influence our comprehension of the universe for years to come. Stellar nurseries, such as the Orion Nebula, play a crucial role in the formation and evolution of galaxies. These vast regions of gas and dust are rich in raw materials essential for star formation. When dense areas within these clouds collapse under their own gravity, they give rise to new stars. The birth of these stars, in turn, influences their surroundings, creating a complex interplay that impacts galaxy evolution. As new stars form, they emit intense radiation and stellar winds. This energetic output can heat up the surrounding gas and dust, triggering further star formation in neighboring regions. A single stellar nursery can ignite a chain reaction, resulting in clusters of stars being born over relatively short periods. This process enriches the interstellar medium with heavy elements produced during stellar nucleosynthesis, contributing to the chemical evolution of the galaxy. These elements are essential for the formation of planets, and they influence the types of physical and chemical processes within the galaxy. Moreover, stellar nurseries are often where massive stars are born. These short-lived giants have dramatic end-of-life scenarios, typically culminating in supernova explosions. These catastrophic events not only distribute heavy elements across the galaxy, but also create shock waves that can compress nearby gas clouds, leading to additional star formation. This dynamic recycling of materials is a fundamental aspect of how galaxies evolve over time. Finally, the gravitational interactions and feedback mechanisms present in regions like the Orion Nebula shape the structure of galaxies. The mass distribution among newly formed stars ultimately influences the galaxy's dynamics, whether it leads to the formation of spiral arms, the triggering of supernovae, or the creation of new stellar systems. The actions taking place in stellar nurseries are interwoven with the broader tapestry of galaxy evolution. Each star born in these nurseries signifies a step in the ongoing story of the universe's development. Magnetic fields play a significant and often underappreciated role in the dynamics of interstellar space. These fields permeate the cosmos and influence various phenomena, from star formation to the behavior of cosmic rays. Interstellar magnetic fields are generated by the movement of charged particles within the plasma of space and are thought to originate from processes occurring in stars and galaxies, including stellar winds and supernova explosions. One of the most compelling roles of magnetic fields is their influence on star formation. As clouds of gas and dust collapse under gravity to form stars, magnetic fields can either support or hinder this process. They can provide a stabilizing effect that prevents the gas from collapsing too quickly, allowing for a slower, more organized formation of stars and planets. However, they can also channel outflows of material during star formation, influencing the distribution of newly created stars and helping to shape the structure of stellar nurseries. Furthermore, magnetic fields are critical for the propagation of cosmic rays, high-energy particles that travel through interstellar space. These cosmic rays are influenced by magnetic fields as they zigzag along their paths, making their behavior intricate and complex. The interaction between cosmic rays and magnetic fields can excite the surrounding medium, leading to the creation of shock waves and contributing to heating in the interstellar medium. This interplay affects the overall dynamics of galactic environments and can have implications for star formation rates and the movement of materials. In addition to their impact on star formation and cosmic rays, magnetic fields play a role in the large-scale structure of galaxies. They can influence the flow of interstellar gas, affect the rotation and overall dynamics within galaxies, and may even play a role in the formation of spiral structures. As astronomers continue to explore the complexities of interstellar magnetic fields, their understanding of the universe's evolution deepens, revealing the intricate connections between magnetic phenomena and various cosmic processes. Supernovae are monumental cosmic events that significantly enrich the interstellar medium with heavy elements. When massive stars exhaust their nuclear fuel, they undergo a dramatic collapse, resulting in an explosion of astonishing energy and luminosity. This catastrophic event marks the end of a star's life cycle and plays a pivotal role in recycling material back into space, both renewing the interstellar medium and enhancing its elemental diversity. During the evolutionary phases leading up to a supernova, massive stars create heavy elements through stellar nucleosynthesis. Inside their cores, they fuse lighter elements into heavier ones, producing elements like carbon, oxygen, and even iron. Once a star runs out of fuel to sustain fusion, the core collapses under gravity, leading to a rebound effect. This explosion ejects the star's outer layers into space at incredible speeds, dispersing the heavy elements formed during its lifetime into the surrounding interstellar medium. The expelled material from a supernova contributes significantly to the gas and dust already present in space. Over time, this enriched material mixes with the existing interstellar medium. As this gas cools and compresses, it can eventually lead to the formation of new stars and planets, which inherit the heavy elements introduced by the earlier generations of stars. This process is vital for cosmic evolution, as it means that stars and later planets are formed from a more complex mix of elements, enabling the formation of structures like rocky planets and the genesis of life. Moreover, supernovae also inject energy into the interstellar medium, creating shock waves that can trigger further star formation in surrounding gas clouds. This feedback effect not only enriches the medium, but also fosters a continuous cycle of birth and death among stars across galaxies. Each supernova thus serves as both a creator and an energizer, fundamentally shaping the chemical landscape of the universe. The intricate relationship between these explosive events and the interstellar medium is a key aspect of understanding cosmic evolution and the origins of the elements that make up everything we see around us. The local bubble is a fascinating feature of our galactic neighborhood that significantly influences the environment in which our solar system resides. This bubble is a roughly 100 light-year wide cavity within the interstellar medium that is largely devoid of the dense gas and dust typically found in other regions of the Milky Way. Instead, it is characterized by a lower density of hydrogen and helium, creating a more vacuum-like condition. Surrounding this bubble, denser regions of gas exist, making the local bubble an intriguing anomaly in our galactic landscape. The origin of the local bubble is believed to be linked to supernova explosions and stellar winds from nearby massive stars. Over the course of millions of years, the high-energy outflows from these celestial forces shaped this cavity, clearing out gas and dust through the combined effects of shock waves and radiation. As a result, the local bubble effectively serves as a sheltered area amid the more chaotic backdrop of the Milky Way, leading to unique conditions for star and planet formation in its vicinity. The local bubble has significant implications for the solar system. One of its effects is the alteration of cosmic ray exposure. Due to the reduced density of matter within the bubble, our stellar neighborhood experiences different levels of cosmic ray bombardment compared to denser areas of the galaxy. This variation in cosmic ray density can influence conditions on Earth and potentially affect biological processes, though the exact impacts are still a subject of scientific investigation. Additionally, the local bubble affects the dynamics of interstellar dust and gas in our vicinity. This area has been instrumental in the formation of structures such as the local interstellar cloud, where our solar system is currently located. The interplay of these factors contributes to the understanding of not just our solar system's past, but also the ongoing processes that shape our cosmic environment. As research continues, the local bubble helps astronomers grasp the complexities of galactic structure and the environments that support stellar systems like ours. Gravitational waves are ripples in the fabric of space-time generated by certain movements of massive objects, such as colliding black holes or neutron stars. When these astrophysical events occur, they create disturbances that propagate outward from their source at the speed of light, traveling across the cosmos and carrying information about their origins. As gravitational waves traverse interstellar space, they interact with the matter present, but because the waves are incredibly weak, their effects on the surrounding environment are minimal. As gravitational waves pass through space, they stretch and compress space-time itself. This means that they can alter the distances between objects in their path, although the effect is so tiny that it is nearly imperceptible unless measured with highly sensitive equipment. For instance, a gravitational wave that passes through Earth may cause minute changes in distance on the order of a fraction of the diameter of a proton, an exceedingly small amount that poses a significant challenge for detection. Gravitational waves can travel through the vast emptiness of interstellar space without being significantly absorbed or scattered. This is because they do not interact with matter in the same way that electromagnetic waves like light do. Therefore, they can journey great distances across the universe, providing a unique means of studying celestial events that might otherwise remain undetectable. This quality allows astronomers to learn about phenomena occurring far beyond the reach of traditional telescopes, unveiling secrets of the universe's most violent and energetic occurrences. The detection of gravitational waves presents a new frontier in astrophysics. By capturing these waves using instruments like the Laser Interferometer Gravitational Wave Observatory LIGO, scientists can analyze the information carried by these ripples, revealing insights about the processes that create them. This emergent field, often referred to as gravitational wave astronomy, not only expands our understanding of events like black hole mergers or neutron-star collisions, but also offers a deeper understanding of fundamental physics and the nature of space-time itself. Each ripple of a gravitational wave resonates a message from the far reaches of the universe, connecting us to cosmic events that shape the very structure of reality. Measuring the size and shape of the Milky Way galaxy from within it presents a unique challenge. While we reside in one of its spiral arms, astronomers have developed several ingenious methods to map our galaxy's structure and dimensions. By combining data from various observational techniques, scientists can piece together a comprehensive picture of our galactic home. One of the primary tools used in this endeavor is the observation of star clusters and stellar populations. By studying the distribution and movements of stars and star clusters, astronomers can infer the galaxy's structure. In particular, measuring the positions, brightness, and distances of stars helps map the spiral arms and the overall flattened disk shape of the Milky Way. For distances, astronomers utilize methods such as parallax, which involves measuring the apparent shift in a star's position as observed from different points along Earth's orbit around the Sun. This technique is especially effective for nearby stars. To achieve a broader view over vast distances, astronomers employ techniques involving variable stars, particularly Cepheid variables. These stars have a well-established relationship between their brightness and the time it takes to complete one cycle of brightness variations. By identifying these stars in different parts of the galaxy and measuring their pulsation periods, astronomers can calculate their distances, contributing to our understanding of the Milky Way's size and shape. Another crucial aspect involves the study of the galaxy's rotation. By examining the Doppler shifts in light from stars and gas clouds, scientists can measure how quickly different regions of the galaxy rotate around its center. This rotational curve helps reveal the presence of dark matter and provides insight into how mass is distributed throughout the galaxy. Combining these measurements creates a comprehensive model of the Milky Way, allowing researchers to determine dimensions such as the galaxy's diameter, the thickness of its disk, and the extent of its halo. Through these multifaceted methods, astronomers gradually unveil the intricate structure of the Milky Way, piecing together a cosmic jigsaw puzzle that reveals the shape of our galaxy and its place in the vast universe. The ongoing exploration of our galactic environment continues to refine our understanding, enhancing our perspective of the cosmos. At the heart of our galaxy lies a supermassive black hole known as Sagittarius A. This enigmatic object possesses a mass equivalent to approximately 4 million times that of our Sun, wrapped in an incredibly dense region of space. The black hole is invisible in visible light, but can be detected through its gravitational influence on nearby stars and gas. Observations of stars orbiting Sagittarius A reveal their high velocities, indicating the presence of a massive object in a confined area. The gravitational pull of the supermassive black hole plays a fundamental role in shaping the structure and dynamics of the Milky Way galaxy. Its presence stabilizes the orbital patterns of stars in the central bulge, ensuring that the stars remain in a rotating disk, like formation around the black hole. This central region is rich in stars, gas, and dust, creating a vibrant area of stellar activity that contrasts with the more tranquil arms of the galaxy. Moreover, the energy emitted from matter spiraling into Sagittarius A influences the surrounding environment. As gas falls toward the black hole, it heats up and emits radiation, which can affect star formation rates in nearby regions. The intense radiation can compress molecular clouds, populating them with new stars. This feedback mechanism creates a dynamic interplay between the supermassive black hole and the growth of stars, further shaping the galactic structure. Additionally, Sagittarius A is part of a broader galactic core, which contains dense concentrations of stars and dark matter. This area, often referred to as the galactic nucleus, contributes to the overall mass distribution and gravitational forces acting throughout the Milky Way. As researchers study the interactions between the supermassive black hole and the surrounding stellar populations, they gain insights into the formation and evolution of galaxies as a whole. The influence of Sagittarius A extends far beyond its immediate vicinity, playing a critical role in the larger narrative of galactic structure and development. The formation and maintenance of spiral arms in galaxies such as the Milky Way is a captivating process rooted in the dynamics of galactic rotation and density waves. Spiral arms are not fixed structures, but are instead dynamic features that emerge from the complex interactions between stars, gas, and dark matter distributed throughout the galaxy. These arms occur in a pattern reminiscent of tightly wound whirlpools, characterized by concentrations of stars and interstellar gas. One prominent theory that explains the emergence of spiral arms is the density wave theory. According to this concept, as stars in a galaxy rotate differentially, with some moving faster and others slower, they create regions of varying density in the galactic medium. These density waves propagate through the disk of the galaxy, acting as a wave that compresses the gas and dust in specific regions. When gas is compressed, it becomes denser, leading to increased star formation. As a result, young bright stars cluster together in these areas, forming the visible spiral arms. The maintenance of the spiral arm structure hinges on the balance between gravitational forces and the dynamical processes occurring in the stellar and gas populations. As stars move through the arms, they experience gravitational interactions with the matter in the arms, which helps keep them in their positions. Simultaneously, stars are also subject to forces that can cause them to gradually shift in their orbits. However, the spiral arm itself moves through the galaxy, allowing for a continual recycling of stellar material that fuels star formation. Over time, interactions with other nearby galaxies can also influence the structure of spiral arms. Tidal forces and gravitational interactions can reshape existing arms, leading to transient features that enrich the overall complexity of a galaxy's structure. As new stars are formed and older stars move away from the arms, the dynamics of these regions ensure that spiral arms continuously evolve, maintaining their characteristic shapes even as individual stars and gas clouds undergo changes. This intricate interplay between gravitational dynamics, star formation, and the behavior of matter within spiral galaxies enables the stunning structures we observe in the cosmos. The concept of the galactic habitable zone holds significant implications for our understanding of where life may arise in the cosmos. Much like the habitable zone around a star, where conditions could allow for liquid water to exist, the galactic habitable zone refers to regions within the Milky Way that are more favorable for the development of life. These areas are characterized by a combination of factors, including the availability of essential elements, stellar density, and the stability of the environment over astronomical timescales. One crucial aspect of the galactic habitable zone is its location. It is generally thought to lie in the Orion arm of the Milky Way, approximately 50,000 to 100,000 light-years from the galactic center. This region strikes a balance between being far enough away from the core, where intense radiation and supernova activity could hinder the development of life, and close enough to benefit from the abundance of heavier elements produced in previous generations of stars. The presence of these elements, such as carbon, nitrogen, and oxygen, is vital for forming planets and ultimately supporting life as we know it. Additionally, the density of stars and the environment within the galactic habitable zone must be conducive to stable planetary systems. Too many nearby stars could lead to gravitational disruptions that destabilize orbits, increasing the likelihood of catastrophic events such as close encounters or collisions. Conversely, a sparsely populated area might limit the opportunities for star and planet formation. Thus, the galactic habitable zone is a region where these conditions align to provide a more stable environment for planetary systems to develop and sustain life. The significance of the galactic habitable zone extends beyond our immediate cosmic neighborhood. It encourages scientists and astrobiologists to consider the broader context of life's potential existence in the universe. By examining the distribution of habitable zones across different types of galaxies and their evolutionary history, researchers can refine their understanding of where we might find extraterrestrial life. This ongoing exploration challenges us to think about life's resilience and adaptability, opening up conversations about the complex interplay of cosmic factors that shape our place in the universe. Globular clusters are dense groups of ancient stars that orbit the Milky Way galaxy. playing a critical role in helping astronomers determine the age and evolution of our galaxy. These clusters, often containing hundreds of thousands of stars, are among the oldest known stellar systems, with ages estimated to be around 11 to 13 billion years. Their formation likely coincided with the early stages of the universe, making them invaluable time capsules that inform our understanding of galactic history. The age of globular clusters can be estimated by studying their stellar populations. Specifically, astronomers examine the color magnitude diagrams of these clusters, which plot the brightness of stars against their color. By identifying the point at which the main sequence of stars begins to turn off a stage in stellar evolution, called the main sequence turnoff, scientists can infer the age of the cluster. As more massive stars evolve more quickly than their less massive counterparts, the stars at this turnoff point provide a clear signature of the cluster's age and, by extension, help estimate the time when the Milky Way began to form its first stars. Globular clusters also shed light on the evolutionary processes of the Milky Way. Their distribution within the galaxy offers insights into the galaxy's formation and dynamical history. For instance, the fact that most globular clusters are found in the halo and not in the disk suggests they formed early in the galaxy's history, before the galactic disk took shape. Observations of their orbits and positions indicate that they may have formed from the remnants of smaller galaxies that merged with the Milky Way, providing a record of the galaxy's interactions and accretions over time. Furthermore, the chemical composition of stars in globular clusters can reveal important information about the early conditions of the Milky Way. Studying the abundance of various elements in these stars helps astronomers understand the processes that enrich the interstellar medium and influence the formation of later generations of stars. This chemical fingerprint offers a glimpse into the history of star formation and the buildup of elements essential for the development of planets and life. The ongoing study of globular clusters continues to provide critical insights into the age, structure, and evolutionary history of our galaxy. These ancient stellar systems serve as a bridge to the distant past, helping us piece together the story of the Milky Way and our place within it. By analyzing the abundance of heavy elements in stars within the Milky Way, astronomers gain insight into the processes of stellar nucleosynthesis and the distribution of these elements across the galaxy. This helps illustrate the timeline of chemical enrichment in the Milky Way and the evolution of star formation over billions of years. The study of globular clusters in particular provides its presence is inferred through the gravitational effects it has on visible matter such as stars and gas. By closely analyzing the dynamics of stellar motion, astronomers can gather vital evidence regarding the shape and extent of dark matter within our galaxy. One primary observation involves the rotation curve of the Milky Way, which describes how the orbital speeds of stars vary with their distance from the galactic center. In a galaxy dominated solely by visible mass like stars and gas, one would expect the rotation speed to decrease with distance from the center, similar to how planets in our solar system move faster when closer to the sun. However, measurements show that the rotation speeds of stars remain relatively constant or even increase slightly at greater distances from the center. This discrepancy implies the existence of additional mass exerting gravitational influence, providing evidence of dark matter extending well beyond the observable components of the galaxy. Astronomers also study the motion of stars in clusters and the positions of satellite galaxies to gather more information about dark matter. The faster-than-expected velocities of stars in these groups suggest the presence of a considerable amount of unseen mass in the form of dark matter halos. These halos surround galaxies, influencing their structure and interactions. By modeling the motion of stars and the gravitational forces at play, scientists can estimate the density and distribution of dark matter within the Milky Way and determine its overall mass. Furthermore, the study of gravitational lensing, where light from distant objects bends around massive objects, is another method that reveals the presence of dark matter. By observing how light is distorted as it passes near the Milky Way and its associated structures, researchers can map the dark matter halo surrounding the galaxy. This technique enhances our understanding of the distribution of dark matter and its role in shaping the evolution of both our galaxy and the universe as a whole. The movement of stars serves as a powerful tool for probing the elusive nature of dark matter within the Milky Way. By analyzing these motions through various observational methods, astronomers continue to refine their understanding of how dark matter influences galactic dynamics, helping to construct a more complete picture of the cosmos and the forces at play within it. Mapping the distribution of interstellar gas and dust within the Milky Way galaxy is a complex yet fascinating process undertaken by astronomers using a variety of observational techniques. These methods allow scientists to visualize where gas clouds and dust exist, enabling a better understanding of the galactic structure and the processes that govern star and planet formation. One primary technique employed in this endeavor is radioastronomy. Interstellar hydrogen gas, particularly in its neutral form, emits radiation at specific wavelengths, notably 21 centimeters. By utilizing radio telescopes to detect this emission, astronomers can trace the distribution of hydrogen throughout the galaxy. The high sensitivity of radio observations allows researchers to map not only the locations of hydrogen clouds, but also their velocity and density, providing insights into the dynamics of the interstellar medium. In addition to radio observations, infrared astronomy plays a crucial role in mapping interstellar dust. Dust particles absorb and scatter visible light, making them difficult to observe in optical wavelengths. However, they emit thermal radiation in the infrared spectrum, allowing astronomers to detect and map these regions effectively. Satellites like the Herschel Space Observatory and the Spitzer Space Telescope have provided detailed surveys of the Milky Way, capturing the infrared emissions from both gas and dust. These observations reveal intricate structures like molecular clouds, star-forming regions, and dust lanes, illuminating the hidden aspects of our galaxy. Furthermore, astronomers utilize the technique of stellar extinction to gather data on interstellar dust. When light from distant stars passes through clouds of dust, some of that light is absorbed and scattered, leading to a dimming effect. By comparing the apparent brightness of stars obscured by dust to those that are not, scientists can estimate the amount of dust in various regions of the galaxy. This method helps paint a more comprehensive picture of the distribution of dust and gas, shedding light on their role in the Milky Way's structure and evolution. Incorporating these various observational strategies, astronomers can construct detailed maps that highlight the intricate web of gas and dust throughout the Milky Way. This understanding is pivotal for studying star formation processes, the dynamic interactions of gas clouds, and the chemical evolution of the galaxy. The ongoing investigation into the interstellar medium remains crucial for comprehending our galactic neighborhood and the broader workings of the universe. The Fermi bubbles are intriguing structures that extend above and below the plane of the Milky Way galaxy, emanating from the galactic center. Discovered through observations by the Fermi Gamma Ray Space Telescope, these roughly spherical bubbles span approximately 25,000 light-years in height and are composed of high-energy particles and gamma-ray emission. Their presence suggests significant and dynamic processes occurring at the heart of our galaxy. The nature of the Fermi bubbles is believed to be closely linked to the activity of the supermassive black hole located at the center of the Milky Way, known as Sagittarius A. While the exact mechanisms are still a subject of research, one prevailing theory posits that the bubbles were formed by powerful jets or outflows of energy and particles resulting from the accretion of gas onto the supermassive black hole. Periods of intense activity, potentially associated with the black hole swallowing nearby matter, could generate jets that propel material away from the core, creating these large bubble-like structures. In addition to their relation to the central black hole, the Fermi bubbles provide insights into cosmic ray propagation and the interstellar medium. The high-energy particles within the bubbles, primarily electrons, emit gamma rays as they interact with the surrounding gas and magnetic fields. Studying the gamma ray emissions helps astronomers understand the processes governing cosmic rays and their interactions within the Milky Way. The bubble's existence also affects the dynamics of the interstellar medium, potentially influencing star formation processes and the distribution of gas and dust in their vicinity. The Fermi bubbles illustrate the dynamic interplay between galactic centers and their surroundings, hinting at the complex history of our galaxy. As research on these structures continues, they serve as a window into understanding the energetic processes that shape the Milky Way and the broader cosmos. Their study contributes to our ongoing exploration of how supermassive black holes influence their host galaxies and the intricate relationships between energy, matter, and the evolution of the universe. Stellar populations within the Milky Way galaxy exhibit remarkable variations across the galactic disk, bulge, and halo, reflecting different evolutionary histories and formation processes. Each of these regions contains distinct characteristics in terms of age, composition, and dynamics, contributing to the overall structure of the galaxy. The galactic disk is home to the majority of younger stellar populations, including open clusters and stars forming in stellar nurseries. This region is rich in gas and dust, facilitating ongoing star formation. The stars in the disk generally have higher metallicities, indicating that they originated from a continuous cycle of star formation and recycling of materials over the past several billion years. The disk also features a well-defined structure with spiral arms populated by recently formed bright stars, along with older stars residing in a more diffuse distribution. In contrast, the galactic bulge is a dense spherical region located at the center of the Milky Way. The stars here tend to be older and have higher metallicities than those found in the disk, likely due to earlier star formation episodes that rapidly created heavy elements. The bulge contains a mixed population of both younger and older stars, though most are older, suggesting they formed early in the galaxy's history. The dynamic activity within the bulge shows that stars follow more random orbits, contrasting with the organized rotation found in the disk. The halo, on the other hand, houses an older population of stars, including globular clusters that are some of the oldest known objects in the galaxy. Stars in the halo are typically metal-poor, indicating they formed from primordial gas that had not yet been significantly enriched by later generations of stars. The halo contains fewer stars overall, and its stellar populations appear to follow more random orbits. It is thought to contain remnants of the early formation of the Milky Way, as well as stars that have been accreted from smaller galaxies. These differences between populations in the disk, bulge, and halo provide key insights into the formation and evolutionary history of the Milky Way. As astronomers continue to study these populations, they unravel the intricate processes that shaped our galaxy and its stellar constituents, revealing the rich narrative of cosmic evolution. The galactic magnetic field plays a crucial role in both star formation and the behavior of cosmic rays within galaxies. These magnetic fields are thought to arise from the motion of conductive materials, particularly in the galaxy's gas and plasma. They influence how interstellar gas collapses to form new stars and regulate the movement and acceleration of cosmic rays through the galaxy. When it comes to star formation, the galactic magnetic field can provide support against gravitational collapse. As dense clouds of gas and dust begin to contract, the magnetic field exerts a force that can inhibit this collapse to some extent, allowing for a more controlled and gradual formation of stars. The field lines can also guide material into rotating structures, which are essential in forming protostars. Without the presence of these magnetic fields, star formation might proceed in a more chaotic manner, leading to fewer stars being born in a given region. Cosmic rays, which are high-energy particles originating from various sources, including supernovae and active galactic nuclei, are also significantly influenced by the galactic magnetic field. As these charged particles travel through the galaxy, they encounter magnetic fields that can affect their trajectories. The magnetic field acts as a sort of cosmic maze, bending and scattering the paths of these particles in ways that can increase their energy and alter the zones where they can be found. This interaction also impacts the diffusion process, as cosmic rays are less likely to escape the galaxy when the magnetic field is strong or complex, affecting how far they can travel into intergalactic space. Furthermore, the dynamics of the galactic magnetic field itself can fluctuate over time. These changes can lead to periodic enhancements in cosmic ray intensities, triggering intricate interactions with the surrounding interstellar medium. This fascinating interplay between cosmic rays and the galactic magnetic field not only influences the life cycle of stars, but also contributes to the overall energy distribution within the galaxy, painting a picture of a dynamic and ever-evolving cosmic landscape. Gravitational interactions between the Milky Way and the Andromeda Galaxy are a fundamental force shaping the structure and dynamics of our cosmic neighborhood. These two galaxies are both part of the Local Group, which consists of over 40 galaxies held together by their mutual gravitational attraction. As Andromeda and the Milky Way draw closer together, their gravitational fields exert significant influences on one another, affecting everything from stellar motion to galactic structure. The Milky Way and Andromeda are on a collision course, projected to merge in about 4 billion years. As they approach each other, their gravitational interactions will affect the orbits of stars and gas within both galaxies. Over time, this interaction can trigger star formation by compressing gas clouds, leading to bursts of new stars as the two galaxies share their material during their approach. This stellar formation can transform the structure of both galaxies, creating new and vibrant regions of activity. Additionally, the merging process will lead to the redistribution of stars and gas. As the galaxies collide, they will pass through each other, and their gravitational fields can create tidal forces that distort their shapes. This deformation can lead to the formation of tidal tails, which are streams of stars and gas that extend outwards from both galaxies. These tidal features can reveal much about the galaxy's interactions and can even become sites of new star formation. Ultimately, the gravitational dance between the Milky Way and Andromeda will reshape not just the two galaxies, but also the entire Local Group. As they merge, other smaller galaxies in the vicinity will also be affected, either being absorbed into the larger systems or disturbed in their own orbits. This grand interaction is a dynamic process that highlights the interconnected nature of galaxies in the universe, showcasing how the gravitational forces at play can give rise to stunning cosmic realities. Studying the dwarf galaxies orbiting the Milky Way provides a wealth of information about our own galaxy, the nature of dark matter, and the evolution of galaxies in general. These smaller companions, such as the large and small Magellanic Clouds, as well as numerous others, offer unique insights into cosmic processes that are difficult to observe in larger galaxies. One of the most significant lessons from dwarf galaxies is their relationship with dark matter. Dwarf galaxies generally have a high proportion of dark matter relative to their visible matter, making them key players in understanding this elusive component of the universe. By analyzing their motion and structure, astronomers can infer the distribution of dark matter in our vicinity. This information is essential for piecing together the role dark matter plays in the formation and stability of galaxies. Moreover, dwarf galaxies often exhibit star formation histories that can vary widely. Some may have actively formed stars in the past, while others have largely ceased star production. By studying these differences, we gain insights into the processes influencing star formation, such as the effects of supernova feedback, gas stripping, and interactions with larger galaxies like the Milky Way. This understanding helps researchers construct a more complete picture of how galaxies evolve over cosmic time. Furthermore, examining the chemical composition of dwarf galaxies can shed light on the early universe conditions. Dwarf galaxies serve as cosmic laboratories, preserving the records of stellar nucleosynthesis and chemical enrichment from their stellar populations. Through detailed observations of their stellar populations, scientists can trace the histories of star formation and the contributions of supernova explosions, which are vital for understanding the life cycle of matter in the cosmos. Studying the companions of the Milky Way not only informs us about local processes, but also complements our understanding of galactic behavior across the universe. These discoveries illuminate the intricate web of interactions that define galaxy formation and evolution, ultimately enhancing our comprehension of the cosmos as a whole. Galactic collisions and mergers play a pivotal role in the evolution of the Local Group, a collection of galaxies that includes the Milky Way, Andromeda, and many smaller galaxies. These dynamic encounters alter the structure and composition of galaxies, leading to significant changes in their formation and development over cosmic timescales. One of the most direct influences comes from the gravitational interactions that happen during these collisions. As galaxies collide, they disrupt each other's gravitational fields, which can lead to the transfer of gas and stars between the galaxies involved. When an event like this occurs, it can trigger intense bursts of star formation as gas clouds are compressed and forced to collapse into new stars. This process not only enhances the stellar populations of the merging galaxies, but also reshapes their overall morphology, often leading to an increase in complexity and dynamic behavior. The merging of galaxies can also result in the formation of larger structures. Over time, smaller galaxies within the local group may be absorbed into larger ones, such as the ongoing process between the Milky Way and its various dwarf companions. These interactions can break apart satellite galaxies, redistributing their stars and gas, which contributes to the growth of the host galaxy. This transformative process is crucial in understanding how galaxies evolve, as it demonstrates how interactions can pave the way for larger systems to form from smaller ones. Moreover, collisions and mergers alter the dynamical relationship among galaxies in the local group. The gravitational influence of one galaxy can affect the orbits and stability of its neighbors, leading to a re-evaluation of the entire structure of the galaxy group. This interconnected evolution creates a cosmic web where each galaxy's fate is tied to the others, influencing star formation rates, gas distribution, and the overall galactic environment. The study of galactic collisions within the local group highlights the complexity of cosmic evolution, illustrating how intergalactic interactions can dramatically shape the galaxies we observe today. Consequently, understanding these events not only provides insights into the history of our local group, but also offers a broader view of galaxy formation and evolution across the universe. The distinct structures of elliptical and spiral galaxies offer valuable insights into their formation, evolution, and the physical processes shaping the universe. These two primary classifications reveal contrasting characteristics that stem from their different histories and environments. By examining these differences, astronomers can better understand the life cycles of galaxies and the roles of various factors in their development. Spiral galaxies, including our Milky Way, are characterized by their flat rotation disks populated with stars, gas, and dust, along with prominent spiral arms. These features indicate ongoing star formation, where the presence of gas leads to the birth of new stars. The spiral structure suggests a high angular momentum, which allows for further star formation as material is drawn into the central parts of the galaxy. Observing spiral galaxies can thus provide clues about the processes and mechanisms fostering starbirth, as well as the effects of interactions with nearby galaxies. Elliptical galaxies, on the other hand, lack the prominent disk structure seen in their spiral counterparts and often appear as smooth, rounded shapes. They tend to have older stellar populations and a significant deficiency of gas and dust, indicating a different evolutionary path. The absence of active star formation suggests that elliptical galaxies went through a phase of rapid star formation followed by a quiescent state where most of the gas was converted into stars, leaving little material for new ones. Understanding the structure of elliptical galaxies can shed light on processes such as gravitational interactions and mergers, which often lead to their formation from the collisions of spiral galaxies or smaller galaxy groups. The different stellar distributions and dynamics within these two types of galaxies also inform our understanding of dark matter and galactic dynamics. Spiral galaxies, with their rotating disks, exhibit pronounced rotational curves that are crucial for studying dark matter's presence and distribution. In contrast, elliptical galaxies typically display more isotropic velocity distributions, which can inform models of how dark matter halos interact with visible matter. By exploring the contrasting structures of elliptical and spiral galaxies, researchers can piece together the intricate puzzle of galaxy evolution, helping to reveal the mysteries of our universe's large-scale structure and the processes that drive cosmic change. Detecting and studying dark matter halos around nearby galaxies is one of the key challenges in modern astronomy. Since dark matter itself does not emit, absorb, or reflect light, astronomers infer its presence through various indirect methods that rely on its gravitational effects. Understanding these halos is essential for comprehending the structure and dynamics of galaxies. One primary technique involves measuring the rotation curves of galaxies. As stars and gas orbit around the center of a galaxy, they should, according to visible matter alone, slow down as they move farther from the center, similar to how planets in our solar system rotate around the sun. However, observations show that the velocities of stars at the outer edges of galaxies remain surprisingly consistent rather than declining. This discrepancy suggests the presence of unseen mass, which we attribute to dark matter halos extending well beyond the visible edge of the galaxy. By analyzing these rotation curves, astronomers can derive the mass distribution of the entire galaxy, including its dark matter halo. Gravitational lensing is another powerful tool employed to probe dark matter. When light from a distant galaxy passes by a foreground galaxy with a significant mass, such as a dark matter halo, the path of the light bends due to the gravitational field. This effect can cause multiple images of the background galaxy to appear or distort its shape. By studying the degree of this lensing, astronomers can determine the mass of the foreground galaxy-S halo and map the distribution of dark matter. Additionally, researchers utilize advanced simulations and models that combine observational data with the theoretical framework of cosmic structure formation. These simulations consider the interplay between dark matter and baryonic matter, the matter that makes up stars, planets, and gas, to predict how galaxies and their halos evolve over time. By comparing simulated results with observations, scientists can refine their understanding of dark matter properties and its role in galaxy formation and evolution. The ongoing quest to study dark matter halos not only enhances our understanding of individual galaxies, but also provides critical insights into the larger cosmic web of structures that shape the universe. As technology and observational techniques advance, astronomers continue to unveil the mysteries surrounding dark matter and deepen our comprehension of its influence on the cosmos. The Magellanic Clouds, consisting of the Large Magellanic Cloud and the Small Magellanic Cloud, are vital for understanding galactic evolution due to their proximity and unique characteristics. These irregular dwarf galaxies orbit the Milky Way and have played a crucial role in providing insights into the processes that govern galaxy formation, interaction, and evolution. Their significance stems from several key aspects of their structure and behavior. One of the most compelling features of the Magellanic Clouds is their interactions with the Milky Way. The gravitational pull exerted by our galaxy has resulted in tidal forces that have shaped the clouds over time. This interaction has led to the stripping and redistribution of gas, making it possible for astrophysicists to study how material flows between galaxies. Observations of star formation in the Magellanic Clouds, especially during bursts triggered by their close encounters with the Milky Way, offer a unique perspective on how gravitational influences can spur new stars. This phenomenon provides a valuable laboratory for exploring star-forming processes that occur during galactic interactions. Additionally, the Magellanic Clouds are home to a diverse array of stellar populations and chemical abundances, reflecting the evolutionary history of these galaxies. By examining the age and composition of stars within the clouds, researchers can piece together a timeline of their formation and development. This information is essential for understanding the role of small galaxies in the larger context of cosmic evolution, particularly as building blocks in the formation of more massive galaxies. The Magellanic Clouds serve as examples of how smaller satellite galaxies contribute to the overall chemical enrichment of their host galaxy through star formation and supernova events. Furthermore, the Magellanic Clouds are crucial for studying the nature of dark matter in nearby galactic structures. Their motion and orbital paths can provide insights into the hidden mass distribution around the Milky Way. By analyzing how the Magellanic Clouds are influenced by the Milky Way's gravitational field, scientists can infer characteristics of the dark matter halo surrounding our galaxy. advancing the understanding of this mysterious component of the universe. Overall, the Magellanic Clouds play a key role in illustrating the interconnected nature of galactic evolution. Their interactions with the Milky Way enhance our understanding of how galaxies behave and evolve, providing essential clues about the processes that shape the cosmic landscape. The insights gained from studying these nearby companions are significant not only for understanding our own galaxy, but also for exploring the broader principles that govern galactic formation and development across the universe. Supermassive black holes, often found at the centers of galaxies, play a critical role in shaping their host galaxy-S structures and dynamics. These colossal entities, typically millions to billions of times the mass of our Sun, exert powerful gravitational forces that influence not only the immediate area surrounding them, but also the entire galaxy. Their effects can be seen in various ways, shaping the behavior of stars, gas, and even dark matter within the galaxy. Supermassive black holes exert profound influence over their host galaxies through interactions with nearby stars and gas. As material spirals into the black hole, it forms an accretion disk, a structure of gas and dust that heats up and emits immense amounts of energy. This process can produce powerful jets and outflows, significantly impacting star formation rates within the galaxy. The energy and momentum released during these events can blow gas away from the central regions, affecting the availability of material needed for new stars. Consequently, the presence of a supermassive black hole can lead to a decrease in star formation in the galaxy-S core and alter the distribution of stars across the galaxy. The influence of supermassive black holes extends beyond their immediate vicinity to the overall gravitational dynamics of the galaxy. Their substantial mass affects the orbits of stars, particularly those in the central regions. This can lead to the formation of a dense cluster of stars near the black hole, enhancing gravitational interactions and dynamic behaviors within the core. The gravitational forces also shape the galaxy-S bulge, influencing its morphology and evolution. Moreover, the relationship between supermassive black holes and their host galaxies is often described by the M-sigma relation. This correlation states that the mass of the supermassive black hole at a galaxy-S center is closely linked to the velocity dispersion of stars in the bulge. This relationship suggests a co-evolution of the black hole and its host galaxy, implying that the growth of supermassive black holes is intimately connected to the processes shaping their galaxies. Understanding the role of supermassive black holes is essential for grasping how galaxies evolve over time. They act as significant drivers of galactic behavior, influencing star formation, structural dynamics, and the interactions of their host galaxies. By studying these enigmatic objects, astronomers can uncover the fundamental processes that govern the evolution of the cosmos, revealing the intricate relationship between supermassive black holes and galaxy formation. The chemical composition of nearby galaxies serves as a valuable tool for unraveling their histories and understanding the processes that have shaped them over time. By analyzing the elements found in stars, gas, and dust within these galaxies, astronomers can infer a wide array of information about their formation, star formation rates, and the effects of interactions with other galaxies. One primary indicator of a galaxy-S history is its metallicity, which refers to the abundance of elements heavier than hydrogen and helium. Newly formed galaxies tend to have low metallicity since they primarily consist of primordial gas. As stars form and evolve, they create heavier elements through nuclear fusion. When these stars eventually die, they expel their enriched material back into the interstellar medium through processes such as supernova and stellar winds. By examining the metallicity of stars within a galaxy, researchers can estimate its star formation history and the extent of stellar evolution, providing insights into how long the galaxy has been forming stars and how effectively it has been recycling material. Furthermore, the distribution of chemical elements across different regions of a galaxy can indicate variations in star formation rates and the effects of feedback processes. For example, regions with high star formation activity may exhibit a different composition than older, less active regions. These differences can reveal the impact of large-scale events such as supernova explosions that redistribute elements throughout the galaxy and trigger further star formation. Understanding these processes is crucial for piecing together the complex history of galaxy evolution. Additionally, studying the chemical composition of nearby galaxies can illuminate the effects of interactions and mergers with other galaxies. When galaxies collide, their gas and stars mix, often leading to enhanced star formation and shifts in chemical abundances. By observing changes in metallicity and element distributions in the aftermath of such events, astronomers can better understand the outcomes of galactic interactions and their contributions to the evolutionary paths of galaxies. The chemical composition of nearby galaxies is a rich source of information that helps astronomers reconstruct the histories of these galaxies. By examining metallicity, elemental distribution, and the impact of stellar and galactic events, researchers can gain insights into the processes that have shaped not only individual galaxies, but also the larger contexts of galaxy formation and evolution across the universe. Intergalactic gas filaments are vast structures that stretch across the cosmos, connecting galaxies and acting as conduits for matter within the local group. These filaments, comprised primarily of hydrogen and helium, play a crucial role in the exchange of gas and influence star formation within galaxies. Their presence helps to illuminate the complex web of interactions that shape the evolution of our cosmic neighborhood. One primary function of these gas filaments is to provide a source of material for galaxies. As galaxies grow and evolve, they consume gas to form new stars. Intergalactic gas filaments can deliver this essential material, especially to smaller or lower-mass galaxies that may struggle to retain gas against their gravitational pull. When galaxies interact with these filaments, they can draw in fresh gas, replenishing their supplies and supporting ongoing star formation. This process helps maintain a dynamic balance within the local group, ensuring that galaxies continue to evolve and contribute to the fabric of the universe. Furthermore, the dynamics of gas filaments can dictate how galaxies interact with one another. The flow of gas along these filaments can shape the environments around galaxies, potentially leading to collisions or mergers. When filaments connect clusters of galaxies, the gravitational interactions can increase the chance of such interactions, allowing for the transfer of stars and gas between nearby systems. These mergers and interactions play significant roles in the evolution of galaxies, influencing their morphology and star formation rates. In addition to star formation, the presence of intergalactic gas filaments can potentially help regulate galactic activity. The cooling and heating of gas as it flows along these filaments can affect the rate at which gas is accreted into galaxies. If a galaxy captures more gas than it can efficiently convert into stars, the excess can be expelled, leading to a reduction in star formation. Conversely, if the flow of gas is adequate, it can rejuvenate and sustain active star-forming regions. This interplay is crucial for understanding how galaxies maintain their structures and dynamics over time. The interactions between intergalactic gas filaments and galaxies in the local group showcase the interconnected nature of cosmic structures. By providing gas, influencing interactions, and regulating star formation, these filaments are integral to the ongoing evolution of galaxies, highlighting the importance of understanding these vast structures in our quest to comprehend the complexity of the universe. Ultra-diffuse galaxies. UDGs are a fascinating class of galaxies characterized by their extremely low surface brightness and vast, faint halos of stars. Despite often possessing a substantial number of stars, these galaxies present a diffuse appearance when viewed from a distance, making them particularly challenging to observe. What sets ultra-diffuse galaxies apart is both their structure and their formation processes, which continue to intrigue astronomers. The defining feature of ultra-diffuse galaxies is their lower-than-expected density of stars compared to typical galaxies of similar mass. UDGs have a much larger size without a corresponding increase in stellar mass, meaning that their stars are spread out over a larger volume, leading to a faint appearance. Many ultra-diffuse galaxies are found within clusters or groups of galaxies, often residing in environments where gravitational interactions can play a significant role in their properties. The formation of ultra-diffuse galaxies is a complex process that likely involves various factors. One prevalent hypothesis suggests that many UDGs form through the depletion of gas and star formation in galaxies that may have previously been more massive. Over time, gravitational interactions within dense environments such as galaxy clusters can strip away gas or stars from these galaxies. This phenomenon, termed Ram pressure stripping, occurs when the hot gas within a galaxy cluster pushes against the denser gas within a galaxy, leading to the removal of fuel needed for star formation. Another possible pathway to the formation of ultra-diffuse galaxies is through mergers and interactions with other galaxies. In such scenarios, smaller galaxies may be absorbed or merged into one another, resulting in systems that spread their stellar content over a larger area. These processes can lead to the formation of UDGs that exhibit similar physical properties. Additionally, some researchers propose that UDGs could arise from the evolutionary effects of dark matter, which governs the gravitational forces in galaxies and can influence star formation rates through compression or heating in dense regions. Ultra-diffuse galaxies are significant for galactic studies because they challenge conventional ideas about galaxy formation and evolution. Their unique characteristics prompt astronomers to reconsider how galaxies can develop in both isolated and dense environments. As the exploration of UDGs continues, they may provide essential insights into the broader processes of galaxy formation and the role of dark matter in shaping the universe's structure. Galaxy clusters are the largest gravitationally bound structures in the universe, consisting of hundreds to thousands of galaxies, dark matter, and hot gas. Their formation and evolution are complex processes influenced by various factors, including gravity, dark matter, and the intergalactic medium. Over cosmic time, galaxy clusters go through several stages of development driven by the interplay of these elements. The formation of galaxy clusters begins with small density fluctuations in the primordial universe, resulting from quantum fluctuations in the early moments after the Big Bang. As the universe expanded and cooled, regions with slightly higher densities began attracting surrounding matter through gravitational forces. Over billions of years, these fledgling structures merged and accumulated more matter, gradually growing into larger protoclusters. As they evolved, clusters continued to merge with smaller clusters and groups of galaxies, falling into larger ones, a process that drives the growth of the cluster. As cluster formation progresses, the gravitational interactions among the galaxies, dark matter, and the surrounding hot gas become increasingly significant. The dark matter component plays a crucial role by providing the gravitational framework that holds the cluster together. It forms a halo surrounding the cluster, affecting its dynamics and the motion of galaxies within it. This dark matter halo increases in complexity over time as mergers occur, enhancing the cluster's overall mass and influencing the orbits of the galaxies it contains. In addition to the gravitational forces, the hot gas found in galaxy clusters plays an essential role in their evolution. As matter falls into the cluster, it accumulates and heats up due to gravitational compression, forming a hot intracluster medium. This medium can emit X-rays, allowing astronomers to study the properties of the gas and the overall structure of the cluster. The gas can also interact with galaxies within the cluster, leading to phenomena such as Ram pressure stripping, where the gas removes stars and gas from the infalling galaxies, thus influencing their evolution. As galaxy clusters mature, they can also exhibit signs of complex dynamics. Major mergers can trigger bursts of star formation in member galaxies or lead to the activation of active galactic nuclei, resulting in phenomena such as radio jets and outflows. Over time, as clusters continue to evolve, they can reach a state of stability characterized by a balance between the gravitational binding of the dark matter, the dynamics of galaxies, and the energy of the hot gas. Understanding the formation and evolution of galaxy clusters is vital for comprehending the large-scale structure of the universe. Clusters serve as laboratories for studying fundamental questions about dark matter, galaxy evolution, and cosmic expansion. By investigating these colossal structures, astronomers gain insights into the history and dynamics of the universe, highlighting the intricate relationships between galaxies and the underlying cosmic framework. Dark matter plays a fundamental role in binding galaxy clusters together, acting as the invisible backbone that influences their structure and dynamics. Comprising approximately 85% of the matter in the universe, dark matter does not interact with electromagnetic forces, meaning it cannot be observed directly through light. However, its presence is inferred through its gravitational effects, which are crucial for the formation and maintenance of galaxy clusters. The gravitational influence of dark matter manifests prominently in the formation of galaxy clusters. As the universe evolved after the Big Bang, regions of space with slightly higher densities began to attract surrounding matter through gravity. This led to the initial formation of protoclusters, small groupings of galaxies and gas that would grow over time. Dark matter, concentrated in halos surrounding these forming clusters, provided the necessary gravitational pull to draw in additional matter. This enabled the clusters to grow in mass, continuously attracting galaxies, gas, and dark matter itself from their surroundings. Once a cluster forms, dark matter continues to exert its influence by acting as a gravitational glue that keeps the cluster bound together. The distribution of dark matter within a cluster is not uniform. It typically forms a spherical or elliptical halo that surrounds the galaxies. This halo provides the majority of the gravitational potential required to hold the galaxies and the hot intracluster gas within the cluster. Observations of the motion of galaxies and the behavior of the gas in the cluster allow astronomers to infer the existence and distribution of dark matter, revealing that it dominates the mass budget of these structures. Additionally, dark matter plays a key role in the dynamics of galaxy clusters. As galaxies orbit within the cluster, they experience gravitational interactions not only with each other, but also with the dark matter halo. This dynamic interplay influences the motion of galaxies, affecting their orbits and velocities. The massive gravitational well created by the dark matter ensures that galaxies remain bound to the cluster rather than drifting away into intergalactic space. This binding effect is particularly important for maintaining the structural integrity of the cluster over cosmological timescales. Dark matter is essential in binding galaxy clusters together through its gravitational influence. It provides the framework that governs the formation, growth, and stability of these massive structures in the universe. By studying dark matter and its effects, astronomers can develop a better understanding of the fundamental forces shaping the cosmos and the intricate relationships between galaxies, gas, and dark matter in the vast expanse of space. The intracluster medium ICM, primarily composed of hot ionized gas, fills the space between galaxies within a galaxy cluster. This medium plays a significant role in influencing the properties of galaxies residing in clusters, affecting their formation, evolution, and overall dynamics. The interactions between galaxies and the ICM can lead to a variety of outcomes, altering how galaxies behave and evolve over time. One of the most profound influences of the intracluster medium is its effect on star formation within cluster galaxies. The hot gas of the ICM can interact with the cold gas in galaxies, providing important feedback mechanisms. For instance, as galaxies move through the ICM at high speeds, they can experience ram pressure stripping. This phenomenon occurs when the pressure exerted by the ICM gas removes or strips away the cold gas from the galaxies. Losing this essential material can severely impact a galaxy ES ability to form new stars, effectively quenching star formation and altering the galaxy S evolution. Galaxies that have undergone significant ram pressure stripping often appear to be passive, with reduced star formation rates compared to their isolated counterparts. Additionally, the temperature and density of the intracluster medium can influence the thermal state of gas within galaxies. The hot gas of the ICM can heat the gas in galaxies through processes such as thermal conduction or shock heating. This increased temperature can prevent gas from cooling and condensing efficiently, thus inhibiting star formation. In contrast, if a galaxy interacts with the ICM in a way that promotes cooling, it can lead to renewed star formation activity in certain regions. The intracluster medium also facilitates a medium for the transfer of energy and momentum. As active galactic nuclei in cluster galaxies emit jets and outflows, the interaction with the ICM can redistribute energy within the cluster environment. This can create complex structures like bubbles or cavities within the hot gas, further influencing the behavior of surrounding galaxies. Such feedback mechanisms can regulate how galaxies accrete gas and how effectively they can form new stars. Moreover, the presence of the intra-cluster medium can contribute to the overall morphology and characteristics of cluster galaxies. For example, galaxies in dense environments may develop elongated shapes or tidal features due to gravitational interactions with the gas and other galaxies. These morphological changes reflect the extensive environmental influences exerted by the ICM and highlight the interconnected nature of galaxies within clusters. The intracluster medium profoundly impacts the properties of galaxies within galaxy clusters by regulating star formation, influencing gas dynamics, and contributing to morphological changes. As astronomers study these interactions, they gain valuable insights into the complexities of galaxy evolution, the effects of the environment on galactic behaviors, and the larger processes that shape cosmic structures. Gravitational lensing by galaxy clusters is a powerful tool that reveals critical information about the distribution of matter, both visible and dark, in the universe. This phenomenon occurs when the gravitational field of a massive object, like a galaxy cluster, bends the path of light from more distant background objects, such as galaxies. This lensing effect allows astronomers to study the mass distribution of the foreground cluster and provides insights into the underlying structure of the universe. One of the principal outcomes of gravitational lensing is the ability to map the total mass of galaxy clusters, including their dark matter components. Since dark matter does not emit light and is difficult to observe directly, its presence must often be inferred through gravitational effects. By analyzing how light from background galaxies is distorted and magnified by a cluster S gravity, scientists can generate a detailed map of the mass distribution within the cluster. This gravitational lensing analysis allows researchers to ascertain how much of the mass is concentrated in dark matter, revealing the significant role it plays in the overall gravitational landscape. There are two main types of gravitational lensing: strong lensing and weak lensing. Strong lensing occurs in cases where the background object is nearly perfectly aligned with the foreground mass, resulting in pronounced distortions such as multiple images or arcs of light. This strong lensing can provide precise measurements of the mass distribution in the core of the cluster. In contrast, weak lensing refers to more subtle distortions of background galaxy shapes, which can be statistically analyzed over broader regions. This method allows astronomers to map the mass distributions of galaxy clusters on larger scales, providing a more holistic view of how matter is distributed in and around these clusters. Gravitational lensing also has implications for understanding the large-scale structure of the universe. By charting the distribution of matter across many galaxy clusters, researchers can gain insights into how matter is organized in cosmic webs and filaments. This information can contribute to our understanding of how galaxies and clusters formed and evolved over time, revealing the interplay between dark matter and baryonic matter in shaping cosmic structures. Furthermore, lensing studies can uncover the effects of environmental influences on galaxy properties within clusters. As researchers assess how background galaxy light is affected by the mass distribution of foreground lensing clusters, they can analyze the relationships between galaxy formation, cluster dynamics, and matter distribution. Gravitational lensing by galaxy clusters serves as a crucial observational tool to map the distribution of matter in the universe. It enables astronomers to measure dark matter, understand large-scale structure, and gain insights into the dynamics between galaxies and their environments, enhancing our comprehension of the cosmos and the forces that govern its evolution. Astronomers employ galaxy clusters as crucial landmarks in determining the universe's expansion rate through a combination of their mass, light, and the behavior of their galaxies. Galaxy clusters are some of the largest structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity, along with vast amounts of hot gas and dark matter. By studying these colossal groups, astronomers can extract valuable information about cosmic distances and the rate of expansion, known as the Hubble constant. One key method involves observing the gravitational lensing phenomenon. Gravitational lensing occurs when massive objects, such as galaxy clusters, bend the light from more distant galaxies behind them. By analyzing the amount of bending and distortion, astronomers can infer the mass of the cluster. This measurement of mass, when correlated with the cluster-S light emissions and the redshift of the galaxies, allows researchers to establish distances and the expansion history of the universe. In addition, astronomers look at the temperature of the hot gas found within these clusters. This gas emits X-rays, and measuring its temperature helps determine how much mass is present in the cluster. By comparing this mass to the cluster-S visible mass from the galaxies, astronomers can apply the well-known relationship between mass and expansion dynamics. These observations lead to a deeper understanding of how quickly the universe is expanding over time. Combining all these observations provides a more comprehensive view of cosmic expansion. This multifaceted approach not only reinforces the findings of previous studies, but also helps refine measurements of the Hubble constant. As astronomers continue to explore these galaxy clusters, their role in the quest to understand the universe's expansion remains vital, revealing ever more about the fabric of our cosmos. The filaments connecting galaxy clusters form a fascinating structure known as the cosmic web, an intricate network that places galaxies and galaxy clusters in a vast tapestry of matter. These filaments are primarily composed of dark matter and ordinary matter, sometimes called baryonic matter, which consists of hydrogen, helium, and other elements. As the universe expanded, gravitational forces led to the formation of these filaments, pulling matter together and creating the large-scale structures we observe today. These cosmic filaments can be visualized as elongated structures that stretch across immense distances, connecting clusters of galaxies like threads in a tapestry. While the vast majority of the filaments are made up of invisible dark matter, they also contain gas that can be seen through various telescopes. This gas often takes the form of diffuse hydrogen, which emits faint radiation, allowing astronomers to study these structures despite their tenuous nature. The interplay between dark matter and baryonic matter within these filaments is crucial for understanding galaxy formation and evolution. As galaxies and clusters gather along these threads, they draw in additional gas and dark matter. This process fuels further star formation and influences the trajectory of galaxies as they grow and evolve. Creatively, these filaments act as highways, providing pathways for galaxies to interact, collide, and form new structures. Studying these filaments gives astronomers insight into the overall distribution of matter in the universe and sheds light on the cosmic microwave background radiation left over from the Big Bang. By analyzing these structures, scientists can learn more about the state of the universe, the nature of dark matter, and the dynamics of cosmic expansion. The cosmic web is an ongoing field of research revealing complexities and surprises that reshape our understanding of how galaxies and clusters are interconnected. Superclusters like Laniakea play a pivotal role in shaping the large-scale structure of the universe. A supercluster is essentially a massive grouping of galaxies, clusters, and galaxy groups bound together by gravity. Laniakea, which includes our own Milky Way galaxy, is particularly significant because it encompasses more than 100,000 galaxies stretching over 100 million light-years. The gravitational pull from such vast collections of mass influences the motion and distribution of galaxies across the universe. The presence of superclusters affects the movement of galaxies as they tend to flow towards these dense regions. This phenomenon is known as gravitational attraction. In the case of Laniakea, its gravitational influence creates a framework that draws in neighboring galaxies from less dense areas. Over cosmic time, this has contributed to the observed clustering of galaxies, forming larger structures while leaving behind vast voids that contain much fewer galaxies. Moreover, superclusters are not just isolated masses, they are part of the interconnected fabric of the cosmic web. The strands of the web are formed by filaments of dark matter, and the density of these filaments tends to increase near superclusters, enhancing the likelihood of galaxy formation and interactions in those regions. Therefore, superclusters serve as the nodes of the cosmic web, where matter collects and galaxies evolve in complex ways, influencing the larger-scale structure we observe today. Studying superclusters also provides insights into the universe's expansion and the overall dynamics of cosmic evolution. By analyzing the distribution and motion of galaxies within superclusters, astronomers can gain a better understanding of the underlying forces that shape the universe. Superclusters like Laniakea offer a window into the vast, interconnected network of galaxies and clusters that define the cosmic landscape. Studying the distribution of superclusters like Laniakea helps astronomers trace the history of cosmic structures back to the early universe, shedding light on how dark energy and gravity interact. These superclusters illustrate the interconnectedness of galaxies on a grand scale, aiding researchers in piecing together the puzzle of the universe's structure and evolution. The temperature and composition of gas within galaxy clusters are crucial indicators of cosmic evolution, revealing insights into the fundamental processes shaping our universe. Galaxy clusters contain vast amounts of hot ionized gas, primarily hydrogen and helium, which can reach temperatures of several million degrees. This extremely hot gas emits X-rays, allowing astronomers to study its properties using space-based observatories such as the Chandra X-ray Observatory. Temperature measurements of cluster gas indicate how much energy has been injected into the gas over time, primarily through processes like supernova explosions and the activity of supermassive black holes. As galaxies merge and collide, they trigger shock waves that heat the gas, increasing its temperature. By analyzing these temperatures, astronomers can infer the history of cluster formation and the energetic events within them, providing clues about the universe's dynamics during its evolution. Additionally, the composition of cluster gas holds critical information about the materials present in the universe. The relative abundance of elements such as oxygen, nitrogen, and iron can be traced back to processes occurring in stars, including nucleosynthesis during stellar life cycles and explosive events like supernovae. By studying these elemental signatures, scientists can gain insight into star formation rates in the universe and how efficiently star materials have been recycled into the intergalactic medium. Together, the temperature and composition of cluster gas allow astronomers to reconstruct aspects of cosmic evolution, such as galaxy formation, clustering patterns, and the interplay between baryonic matter and dark matter. Understanding these factors enhances our knowledge of how the universe transitioned from a hot, dense state shortly after the Big Bang to the complex structures we observe today, revealing intricate connections between galaxies, clusters, and the universe as a whole. Radio galaxies are fascinating objects that emit significant amounts of radio frequency radiation, often accompanied by powerful jets of charged particles. These jets can stretch across vast distances, even surpassing the size of their host galaxy. When these jets interact with the surrounding intracluster medium, they play a crucial role in shaping the environment of galaxy clusters. The intracluster medium is the hot, diffuse gas between galaxies in a cluster, primarily composed of plasma with temperatures reaching millions of degrees. When the relativistic jets from radio galaxies penetrate this medium, several interactions occur. As these jets travel through the intracluster gas, they create shock waves, compressing the surrounding material and heating it further. This process generates turbulence within the intracluster medium, enhancing the mixing of gas and contributing to the overall thermal energy of the cluster. Moreover, the radio jets contribute to the energy budget of the intracluster medium. The energy carried by these jets can efficiently heat the gas, counteracting cooling flows that might otherwise lead to significant loss of hot gas in the cluster. Without this heating, the cooling of the intracluster medium could facilitate rapid star formation in the cluster-S galaxies, altering the cluster-S dynamics and evolutionary path. Additionally, the interaction between radio galaxy jets and the intracluster medium may influence the growth and evolution of galaxies within the cluster. The energy deposition from the jets can regulate star formation in neighboring galaxies, leading to a balance between star formation and suppression. Understanding these interactions provides essential insights into the complex processes affecting galaxy clusters and contributes to our overall knowledge of cosmic evolution. The significance of galaxy cluster collisions, such as the Bullet Cluster, lies in their ability to provide profound insights into the nature of dark matter, galaxy formation, and the overall dynamics of the universe. The Bullet Cluster is particularly compelling because it resulted from a high-velocity collision between two galaxy clusters, leading to an observable separation of normal baryonic matter and dark matter during the interaction. One of the most important revelations from studying the Bullet Cluster is its contribution to our understanding of dark matter. Observations reveal that following the collision, the visible matter, primarily in the form of hot gas, lags behind the bulk of mass detected through gravitational lensing, indicating the presence of dark matter. This separation suggests that dark matter interacts primarily through gravity, while baryonic matter interacts electromagnetically. This allows researchers to infer properties of dark matter and its behavior under extreme conditions not observable in more tranquil scenarios. Galaxy cluster collisions also provide an excellent laboratory for examining the large-scale structure of the universe and the dynamics facilitating galaxy growth and evolution. The energetic collisions can trigger shock waves that compress the intra-cluster medium, leading to temperature changes and a cascading effect on star formation rates in member galaxies. By studying these dynamic systems, astronomers gain insight into the processes that affect galactic formation and transformation. Furthermore, events like the collision of the Bullet Cluster help refine cosmological models, particularly regarding the expansion of the universe. The mass distribution derived from observations allows scientists to test theories of gravity and dark energy, providing a clearer understanding of how the universe evolves over time. In this way, cluster collisions offer a unique perspective on fundamental questions about the cosmos and help deepen our understanding of the universe's composition and behavior. Cosmic voids are vast regions of space that contain very few galaxies, making them some of the largest structures in the universe. These voids play a significant role in the overall architecture of the cosmos. They form through processes linked to the gravitational dynamics of matter in the universe. Early in cosmic history, following the Big Bang, matter was distributed relatively uniformly. However, as the universe expanded and cooled, small fluctuations in density initiated the process of gravitational attraction. Over time, these density fluctuations led to the formation of denser regions where galaxies and galaxy clusters would emerge, eventually evolving into the clumps we see today. The areas surrounding these dense regions, where matter is less concentrated, gradually became cosmic voids as gravity pulled matter toward denser areas, resulting in the formation of large, empty spaces. Cosmic voids are crucial for understanding the large-scale structure of the universe. They are the interstitial areas of the cosmic web, where filaments of dark matter and baryonic matter connect dense clusters and superclusters. This interconnected framework creates a balance, making voids an essential component that helps define the structural evolution of the universe. Their presence influences the movement of matter and the distribution of galaxies, guiding them along the filaments where gravitational forces are stronger. Cosmic voids contribute to our understanding of cosmology, particularly regarding the nature of dark energy and the universe's expansion. By studying voids and their properties, astrophysicists can gain insights into how matter behaves on large scales and the degree of homogeneity and isotropy in the universe. The study of these expansive regions further enhances our comprehension of the formation and evolution of cosmic structures over time. The distribution of galaxies serves as a crucial window into the early universe, offering insights into the initial conditions and processes that led to the formation of cosmic structures we observe today. When astronomers map the positions of galaxies across vast distances, they can analyze patterns that reveal how matter has clustered under the influence of gravity over time. This clustering provides a snapshot of the overall distribution of mass in the early universe, ultimately informing our models of cosmic evolution. In the initial moments after the Big Bang, the universe was nearly uniform and very hot, with slight fluctuations in density. These variations laid the groundwork for later structures to form. As the universe expanded and cooled, the denser regions began to attract surrounding matter, leading to the emergence of galaxies and groups. By studying the distribution of these structures, particularly at greater distances where we observe light from earlier epochs, researchers can trace the timeline of galaxy formation and understand how the seeds of structure were sown in the early universe. The cosmic microwave background radiation, the afterglow of the Big Bang, also provides fundamental clues about galaxy distribution. Observations of this radiation reveal tiny temperature fluctuations resulting from density variations. By correlating these fluctuations with the current large-scale distribution of galaxies, astronomers enhance their understanding of how the universe transitioned from a hot, homogeneous state to the complex, large-scale structure evident today. Additionally, analyzing the distribution of galaxies informs theories about dark matter and dark energy. The patterns of clustering and the observed voids between galaxies offer critical clues to the dynamics of unseen matter and energy that govern cosmic evolution. Ultimately, the distribution of galaxies serves as an essential tool for reconstructing the history of the universe, providing a deeper understanding of the processes that shaped its intricate structure. Baryon acoustic oscillations. BAOs are an important relic from the early universe that act as a standard ruler for measuring cosmic distances. These oscillations originated during the era of recombination, when electrons combined with protons to form neutral hydrogen, allowing photons to travel freely. Before this moment, the universe was a hot, dense plasma of particles that interacted frequently. As the temperature fell, pressure waves or sound waves traveled through this plasma, creating regions of varying density. When the universe expanded and cooled further, the density fluctuations led to the formation of galaxies and clusters in specific patterns. The distance between the peaks of these density fluctuations corresponds to the size of the sound horizon at that time, approximately 150 million light-years. This established a characteristic scale that can be observed in the distribution of galaxies across the universe. When observing large-scale structures, astronomers can detect this characteristic BAO scale in the clustering of galaxies. This consistent distance marker acts like a ruler in cosmic measurements. By studying how galaxies are distributed in three-dimensional space, researchers can compare the observed distance to the predicted scale based on the physics of the early universe, leading to precise measurements of cosmic distances. Using baryon acoustic oscillations, scientists can also constrain cosmological parameters such as the expansion rate of the universe, the nature of dark energy, and the overall geometry of the universe. The consistency of this standard ruler across different regions allows for robust tests of cosmological models, enhancing our understanding of the universe's structure and history. As a result, baryon acoustic oscillations are vital in unraveling the mystery of cosmic expansion and the composition of the universe. The cosmic web is the large-scale structure of the universe, characterized by a vast network of interconnected filaments of dark matter and gas. This intricate framework consists of dense regions known as galaxy clusters and superclusters, connected by elongated filaments and separated by expansive voids. The cosmic web embodies the gravitational effects of dark matter, which makes up a substantial portion of the universe's mass, influencing the formation and distribution of galaxies. At its core, the cosmic web is shaped by the fundamental gravitational attraction of matter. Shortly after the Big Bang, matter was distributed relatively uniformly. Over time, however, slight density fluctuations allowed gravity to pull matter together into clumps. As these clumps merged and grew larger, they formed the dense regions we observe as clusters, surrounded by filaments of less dense material. This process leads to an ongoing cycle of galaxy formation and evolution as structures continue to interact gravitationally. The cosmic web evolves in response to intricate dynamics, including interactions between galaxies, the inflow of gas along filaments, and the role of dark energy, which drives the accelerating expansion of the universe. As galaxies within clusters collide and merge, they can trigger bursts of star formation or create feedback mechanisms that influence their surroundings, further shaping the web's structure. The filaments themselves facilitate the inflow of gas, allowing for the growth of galaxies and clusters and impacting their evolutionary pathways. As the universe continues to expand, the cosmic web experiences changes in density and structure. New galaxies and clusters form, while existing ones evolve through mergers and interactions. Cosmic voids may expand, and the overall morphology of the cosmic web slowly transforms. Studying the nature and evolution of the cosmic web provides essential insights into the processes that govern galaxy formation, the distribution of dark matter, and the dynamics of cosmic expansion. Understanding the cosmic web is key to unraveling the mysteries surrounding the large-scale structure of the universe. Astronomers map the large-scale structure of the universe by employing various sophisticated observational techniques and tools that allow them to survey vast distances in space. One primary method involves observing the distribution of galaxies and galaxy clusters across the sky. By cataloging their positions and redshifts, astronomers can create three-dimensional maps that reveal the arrangement and clustering of matter. To measure the redshift, which is the shift of light from galaxies toward longer, redder wavelengths due to the expansion of the universe, astronomers utilize spectroscopy. This technique involves splitting light from distant galaxies into its constituent colors, allowing them to determine how fast the galaxies are moving away from us. By compiling data from numerous galaxies, astronomers can chart their positions and velocities, contributing to a more comprehensive understanding of cosmic structure. Another essential technique involves using large cosmic surveys, such as the Sloan Digital Sky Survey or the Dark Energy Survey. These projects systematically map millions of galaxies, collecting data on their brightness, colors, and distances. By analyzing the clustering patterns of these galaxies, astronomers can identify underlying structures in the universe and observe phenomena such as cosmic voids, filaments, and clusters. Gravitational lensing is also an invaluable tool in mapping the universe. When massive objects like galaxy clusters bend the light from objects behind them, they create distortions that can be studied to infer the mass and distribution of dark matter. By combining various data sets from galaxy positions, redshifts, and gravitational lensing effects, astronomers can piece together a detailed picture of the large-scale structure. Together, these methodologies enable astronomers to construct expansive maps of the universe, revealing the intricate web of galaxies and their relationships. These maps enhance our understanding of cosmic evolution, dark matter, dark energy, and the dynamics governing the universe we inhabit. As technology and observational techniques continue to improve, astronomers will be able to refine these maps, shedding light on the complexities of the cosmos. Studying the properties of galaxies located at the edges of cosmic voids provides valuable insights into galaxy evolution, the influence of environmental factors, and the overall structure of the universe. These regions represent a unique intersection where dense clusters of galaxies transition into vast empty spaces, allowing astronomers to observe how different environments affect galaxy characteristics and behaviors. One key aspect of these edge galaxies is how their formation and evolutionary processes are influenced by the surrounding cosmic void. In regions closer to dense clusters, galaxies often experience increased interactions, such as mergers and gravitational forces, which can induce bursts of star formation. In contrast, galaxies at the edges of voids generally experience less gravitational influence, leading to a more isolated environment. This allows researchers to study the effects of lower density conditions on star formation rates, morphology, and chemical composition, providing a clearer understanding of how galaxies develop in varying surroundings. These galaxies can also show evidence of being affected by environmental effects, such as ram pressure stripping. As galaxies move through the sparse material in voids, they can lose their gas content, affecting their ability to form new stars. Observing the properties of edge galaxies allows astronomers to ascertain how these environmental influences interact with intrinsic factors to shape galaxy evolution, leading to a better understanding of the conditions necessary for sustained star formation. Furthermore, studying galaxies at the edges of cosmic voids can illuminate the nature of dark matter and its role in structuring the universe. The dynamics of galaxy motions and their spatial distribution in these low-density environments can help astronomers test cosmological models and understand how dark matter clusters work. leading to deeper insights into the interaction between visible and invisible matter in the universe. Overall, through detailed observations of galaxies at the fringes of cosmic voids, astronomers can unravel the complexities of galaxy formation and evolution, improve models of structure formation in the universe, and gain a more nuanced perspective on the interplay between cosmic environments and galactic properties. The presence of dark energy has a profound impact on the growth of cosmic structures by influencing the expansion rate of the universe. Dark energy is thought to make up approximately 70% of the total energy density of the universe, acting as a repulsive force that accelerates the expansion. This acceleration affects how galaxies and galaxy clusters evolve over cosmic time, ultimately shaping the large-scale structure of the universe. In the early universe, gravity dominated the formation of cosmic structures as matter began to clump and form galaxies and galaxy clusters. Gravitational attraction worked to bring these structures together. However, as dark energy became increasingly influential, it began to counteract the effects of gravity on large scales. This means that while structures continued to grow under the influence of gravity, the rate of growth slowed as the expansion of the universe accelerated. As the universe expands at an accelerating rate due to dark energy, the formation of new structures may be hindered. The distance between galaxies increases, making it more challenging for them to interact and merge. This can lead to fewer new galaxies forming and a shift in the movement of existing galaxies. In regions where structures are already formed, gravity still plays a crucial role, but the overall dynamics of how these structures cluster can be altered by the presence of dark energy. Furthermore, dark energy influences the arrangement of cosmic structures such as galaxy clusters and superclusters. The acceleration can lead to variations in how tightly these structures are bound together, potentially affecting the distribution of galaxies and the large-scale cosmic web. By studying the clustering of galaxies and the distribution of cosmic structures, astronomers can gather crucial information about the properties of dark energy and how it reconciles with our understanding of the universe's expansion history. Overall, dark energy plays a pivotal role in shaping the fate of the universe, affecting the growth and evolution of cosmic structures by counteracting the attractive force of gravity. Understanding these interactions remains a central focus in modern cosmology, offering crucial insights into the fundamental forces at work in our cosmos. The Sloan Great Wall is one of the largest known cosmic structures, showcasing the vastness and complexity of the universe. Discovered through extensive mapping as part of the Sloan Digital Sky Survey, this enormous cosmic filament consists of a massive collection of galaxies and galaxy clusters stretching over 400 million light-years. The significance of such large structures extends beyond their sheer size. They provide crucial insights into the nature of cosmic evolution and the fundamental forces that shape our universe. One of the key aspects of the Sloan Great Wall is its role in studying the large-scale distribution of galaxies. By examining how galaxies are arranged in massive structures like this wall, astronomers can better understand the dynamics of gravitational attraction and the clustering of matter in the universe. These observations help confirm the predictions of cosmological models regarding the behavior of dark matter and how it influences the formation of large-scale structures. Moreover, the Sloan Great Wall and similar massive structures challenge our understanding of cosmic homogeneity. The cosmological principle posits that the universe is uniform on large scales, yet the presence of prominent structures suggests regions of density variance. This raises questions about how these structures fit within the framework of an expanding universe governed by dark energy and dark matter. Large structures like the Sloan Great Wall also provide a unique opportunity to study the environments where galaxies form and evolve. The interactions among galaxies within these vast collections can influence star formation rates and the characteristics of galaxies. By studying how galaxies behave in such dense environments, astronomers can glean valuable information about the processes that drive galaxy evolution across cosmic time. The significance of the Sloan Great Wall and similar massive structures lies in their ability to reveal fundamental cosmic processes, challenge existing paradigms, and enhance our understanding of the universe's architecture. They serve as benchmarks for testing cosmological theories and provide a deeper view of the intricate tapestry that constitutes the cosmos. Simulations of cosmic structure formations serve as powerful tools for understanding how the universe evolves, allowing scientists to predict the arrangement and behavior of galaxies and clusters over cosmic time. These simulations incorporate the laws of physics, particularly gravity, thermodynamics, and the dynamics of particles, to model the complex interactions of dark matter, baryonic matter, and energy. By comparing the outcomes of these simulations to observational data, astronomers can validate theories of structure formation and refine models of the universe's evolution. The movement of charged particles within hot ionized gas is indicative of the presence and intensity of magnetic fields in galaxy clusters. Observations show that the strength of these magnetic fields can vary significantly, often influenced by the properties of the surrounding medium. In regions with particularly strong galaxy alignments, researchers may find evidence of active dynamo processes, which generate and strengthen these fields over cosmic time. This alignment phenomenon not only provides clues about the magnetic fields, but also opens avenues for understanding the evolution of the universe. By studying these interactions, scientists can better grasp the complex processes that have shaped the large-scale structure of the cosmos and gain insights into the fundamental nature of gravity, dark matter, and the unseen forces at play throughout the universe. Detecting and studying the cosmic microwave background radiation requires sophisticated technology and meticulous methodology. This faint afterglow of the Big Bang permeates every corner of space. To observe this ancient radiation, scientists use highly sensitive instruments capable of detecting the microwave wavelengths it emits, typically around 2 mm. Space-based observatories have proven particularly effective for this task. The Wilkinson Microwave Anisotropy Probe, launched in 2001, and the Planck satellite, which began operations in 2009, are prime examples. These satellites are equipped with specialized detectors designed to capture the faint signal of the cosmic microwave background without interference from Earth's atmosphere. They meticulously map fluctuations in the radiation, revealing tiny temperature variations that hold vital clues about the early universe's conditions. The data collected from these instruments allows researchers to create detailed maps of the cosmic microwave background's temperature and polarization. These measurements help scientists identify the density fluctuations that ultimately led to the formation of galaxies and large-scale structures. They can also provide insights into the universe's expansion rate, composition, and even its current rate of acceleration, offering a glimpse into the fundamental forces shaping cosmic evolution. Studying the cosmic microwave background radiation has uncovered remarkable information about the universe's age, estimated to be approximately 13.8 billion years. This ancient relic is a key pillar of cosmology, greatly enhancing our understanding of the cosmos and the processes that govern its development. As technology continues to advance, our ability to probe deeper into the background radiation will likely unveil even more about the universe's early moments and subsequent evolution. Temperature fluctuations in the cosmic microwave background radiation serve as a crucial window into the early universe, revealing vital information about its origins and evolution. These tiny variations in temperature, often mere 1 part in 100,000, reflect differences in density and gravitational potential that existed shortly after the Big Bang. Each fluctuation carries a record of the cosmic conditions when the universe was merely a few 100,000 years old. These fluctuations can be analyzed to understand how matter was distributed throughout the early universe. Regions of slightly higher density eventually evolved into galaxies and galaxy clusters, while less dense areas became vast cosmic voids. By mapping these fluctuations, scientists can reconstruct the large-scale structure of the universe as it began to form. This analysis not only sheds light on the distribution of matter, but also provides clues about the influence of dark matter, which plays a significant role in structure formation. Moreover, temperature fluctuations provide insights into fundamental cosmic parameters. For instance, the size of the fluctuations corresponds to the speed of sound in the early universe and the rates of expansion. By studying these patterns, cosmologists can estimate critical values such as the Hubble constant, which describes the rate at which the universe is expanding, and the curvature of space, offering a perspective on whether the universe is flat, open, or closed. In addition to structural insights, the cosmic microwave background also hints at the physics that governed the very early universe, including inflation, a rapid expansion that occurred within the first moments after the Big Bang. The slight variations in temperature we observe today provide evidence of different modes of gravitational waves generated during that time, offering a unique connection to the cosmic events that shaped everything we observe in the universe today. The formation of the first stars and galaxies marks a pivotal moment in the evolution of the universe, occurring after what is known as the Cosmic Dark Ages. This period followed the initial expansion and cooling after the Big Bang, when the universe was filled with neutral hydrogen and helium gas, and no light was emitted from stars. As the universe continued to expand, gravity began to play a crucial role in clumping this primordial matter together. Over time, regions of slightly higher density in this primordial gas began to attract more matter under the influence of gravity. As material accumulated, these clumps formed proto-galaxies. The process relied on the cooling of gas through radiation, allowing the temperature to drop sufficiently for conditions to favor the formation of denser regions. Once these densities became high enough, they initiated nuclear fusion, igniting the first stars, often referred to as population 3 stars. These stars were massive and mostly composed of hydrogen and helium. The intense heat and pressure from these early stars generated energy and radiation that heated the surrounding gas. This environment enabled star formation to proliferate and also led to the reionization of the universe, marking the end of the cosmic dark ages. The ultraviolet light emitted by these first stars ionized the neutral hydrogen, allowing photons to travel freely across space and thereby illuminating the universe. The first galaxies began to form as these stars clustered together. Over time, interactions between stars and mergers between proto-galaxies led to the development of more complex structures. These early galaxies played a monumental role in enriching the universe with heavier elements through processes like supernova explosions, contributing to the chemical evolution necessary for the later formation of more diverse star systems, including our own Milky Way galaxy. The legacy of these first galaxies continues to resonate throughout the cosmos, influencing the structure we observe today. Cosmic inflation is a theory that describes a rapid exponential expansion of the universe during the very first moments after the Big Bang, specifically between 1036 seconds and 1032 seconds. This brief period of inflation is believed to have caused the universe to expand at an astonishing rate, stretching regions of space that were previously subatomic to scales larger than galaxies within a fraction of a second. This theory helps explain several key questions in cosmology, such as the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. One of the primary pieces of evidence supporting cosmic inflation comes from observations of the cosmic microwave background radiation. The fluctuations in temperature and polarization patterns in this radiation match predictions made by inflationary models. These models suggest that the early rapid expansion would imprint specific characteristics on the cosmic microwave background, such as the distribution of hot and cold spots observed today. The precise measurements from experiments like the Planck satellite have reinforced this idea, showing a level of uniformity that would be unexpected without inflation. Another significant piece of supporting evidence is the large-scale structure of the universe. The theory of inflation predicts that very small quantum fluctuations that occurred during inflation would grow over time, leading to the formation of galaxies and clusters. The observed distribution of galaxies across vast cosmic scales aligns remarkably well with these predictions, suggesting that inflation played a critical role in shaping the structure of the present universe. Additionally, inflationary models predict the existence of gravitational waves generated during the rapid expansion. While direct detection of these waves remains an ongoing endeavor, experiments aim to uncover subtle signals in the cosmic microwave background that could provide evidence of inflation's imprint. The search for these gravitational waves could add another robust layer of support to the inflationary scenario, helping to solidify our understanding of the universe its earliest moments. Primordial gravitational waves are ripples in space-time generated during the extremely energetic processes of the universe's infancy, specifically during the period of cosmic inflation. These waves, produced by fluctuations in density and energy as the universe expanded, carry crucial information about the conditions that existed shortly after the Big Bang. Their detection would offer an unprecedented glimpse into the earliest moments of the universe, revealing details that are otherwise unreachable by traditional observational methods. The significance of primordial gravitational waves lies in their ability to encode information about the processes occurring during inflation. These waves are predicted to have a spectrum that relates to the energy scale of inflation, allowing scientists to infer the physical conditions that prevailed during that time. By analyzing the characteristics of these waves, cosmologists can gain insights into the potential mechanisms driving inflation and better understand the fundamental forces at play in the early universe. Researchers look for signatures of primordial gravitational waves in the cosmic microwave background radiation, particularly in its polarization patterns. The B-mode polarization, a specific arrangement of the polarization of light, is a key observable that could be influenced by gravitational waves. If detected, these B modes would confirm the existence of gravitational waves and provide direct evidence of the inflationary epoch. Current experiments, such as those conducted by the BICEP and Polar Bear projects, are diligently seeking to uncover these faint signals, hoping to provide a clearer picture of the universe's birth. Detecting primordial gravitational waves would not only validate theories of inflation, but also enhance our understanding of the early universe's dynamics. This could lead to new insights into fundamental questions about the origins of matter, the forces that shape the cosmos, and even the overall structure of space and time. As such, the ongoing quest for these elusive waves represents a significant frontier in contemporary cosmology. Baryon asymmetry refers to the observed imbalance between baryons particles such as protons and neutrons and antibaryons, their corresponding antiparticles in the universe. This asymmetry is significant because it poses a fundamental question about the nature of the universe. If the Big Bang produced equal amounts of matter and antimatter, why do we observe a universe predominantly composed of matter? Understanding this imbalance can shed light on the processes that occurred in the early universe and potentially reveal new physics beyond the standard model of particle physics. The significance of baryon asymmetry extends to the very fabric of the cosmos. If antimatter had been produced in equal measure during the Big Bang, matter and antimatter would have annihilated each other upon contact, resulting in a universe devoid of stable matter. The existence of stars, galaxies, and even planets are all products of baryonic matter, making the asymmetry crucial for the structural formation of the universe we observe today. Without sufficient baryon asymmetry, the building blocks for the universe as we know it would not exist. Several theoretical frameworks have been proposed to explain this baryon asymmetry, one of which is the Sakharov conditions. These conditions suggest that certain processes must take place to generate an excess of baryons over antibaryons. These processes include baryon number violation, C and CP symmetry violation, and interactions out of equilibrium. High-energy particle colliders and experiments are designed to explore these conditions and search for the mechanisms that could have created the excess of baryons in the early universe. Ongoing research continues to examine potential sources of baryon asymmetry, including interactions involving neutrinos, phase transitions in the early universe, and implications from models of inflation. Understanding baryon asymmetry could unlock answers to profound cosmic questions, encompassing our knowledge of fundamental particles and forces, the nature of dark matter, and the overall evolution of the universe. Each step in this research not only strives to elucidate the history of matter's dominance, but also enhances our grasp of the universe's intricate workings. The process of reionization transformed the early universe by transitioning it from a neutral state to one where hydrogen atoms were ionized, allowing light to travel freely through space. This transformation occurred after the cosmic dark ages, a period when the universe was filled with neutral hydrogen and did not emit any significant light. Reionization is believed to have taken place approximately 600 million to 1 billion years after the Big Bang, marking a critical phase in the evolution of the cosmos. As the first stars and galaxies formed, they began emitting ultraviolet radiation, which was potent enough to ionize the surrounding hydrogen gas. This ionization process involved stripping electrons from hydrogen atoms, resulting in an increase in free electrons and protons. As these ancient celestial bodies, known as Population 2 stars and early galaxies, grew in number, they collectively contributed to the ionization of vast regions of space. This process illuminated the universe, enabling photons to travel unobstructed across the newly ionized regions. Reionization had profound implications for the universe's structure and evolution. It marked the end of the cosmic dark ages and initiated the epoch of structure formation. As neutral hydrogen became ionized, it also influenced the formation of larger cosmic structures by altering gravitational interactions among gas and dark matter. The radiation from early stars and galaxies facilitated the merging of gas clouds, leading to the formation of larger galaxies and clusters over time. Observing the effects of reionization provides critical insights into the cosmos' development. Telescopes such as the Hubble Space Telescope and the upcoming James Webb Space Telescope aim to explore this era further by studying the light from early galaxies and their impact on the surrounding medium. Understanding reionization aids researchers in piecing together the timeline of cosmic evolution, as well as the roles that dark matter and baryonic matter played in shaping the universe we inhabit today. This transformative phase ultimately set the stage for the rich tapestry of cosmic structures we observe in the contemporary universe. Quasars are among the most powerful and luminous objects in the universe, serving as valuable beacons for understanding conditions in the young universe. A quasar, or quasi-stellar object, is an extremely bright and distant active galactic nucleus powered by a supermassive black hole consuming surrounding gas and dust. When material spirals into the black hole, it heats up and emits immense amounts of electromagnetic radiation, often outshining entire galaxies. Their extraordinary brightness allows them to be observed across great distances, making them essential tools for probing the early universe. One of the key insights quasars provide is information about the state of the universe when they were formed. Many observed quasars date back to a time when the universe was only a few billion years old, indicating that supermassive black holes were able to grow rapidly during this period. By studying the properties of these quasars, scientists can glean insights into the formation and evolution of galaxies and black holes in the early universe. The presence of massive black holes so early challenges our understanding of how these objects could accumulate enough mass in a relatively short cosmic time frame. Quasars also shed light on the reionization era. As their intense radiation streams into the surrounding space, it interacts with intergalactic gas, influencing its ionization state. By examining how the light from distant quasars changes as it travels through the universe, scientists can study the distribution and characteristics of the intergalactic medium. This allows for an understanding of how and when reionization occurred, as well as the role of quasars in this significant transformation. Additionally, quasars serve as cosmic markers, helping to map the large-scale structure of the universe. Their light can be used to probe the expansion of the universe and the distribution of dark matter. Observations of quasar light have revealed variations in the cosmic density field, providing clues about how matter has evolved over billions of years. Overall, quasars offer not just glimpses of individual cosmic events, but also a broader context for understanding the dynamic processes and conditions that characterize the young universe. Astronomers study the epoch of recombination through a combination of observational techniques and theoretical models. This significant period in cosmic history occurred approximately 370,000 years after the Big Bang, when the universe cooled sufficiently for protons and electrons to combine and form neutral hydrogen atoms. This process allowed photons to decouple from matter, leading to the release of the cosmic microwave background radiation that we observe today. One of the primary methods astronomers use to study this epoch is by analyzing the cosmic microwave background radiation itself. Advanced telescopes, such as the Planck satellite, have mapped the temperature fluctuations and polarization patterns of the cosmic microwave background with remarkable precision. By examining these fluctuations, researchers can glean information about the density and structure of matter in the universe at the time of recombination. The patterns of these fluctuations provide insights into the conditions of the early universe, such as temperature, composition, and expansion rate. Another important aspect of studying the epoch of recombination is the use of theoretical models based on the physics of quantum fluctuations and fluid dynamics. Cosmological simulations allow scientists to recreate the conditions of the early universe, helping to understand how matter behaved during that era. By comparing the predictions of these simulations with observational data, researchers can refine their models and obtain a clearer picture of what occurred during recombination. Additionally, astronomers utilize spectroscopy to analyze the light from distant objects. When light from early galaxies passes through the intergalactic medium, it interacts with neutral hydrogen and can provide key information about the state of matter at that time. Studies of Lyman alpha emission lines produced by transitions of electrons in hydrogen can reveal details about the universe's ionization state and the effects of recombination. Together, these observational and theoretical approaches allow astronomers to piece together a coherent narrative of the epoch of recombination and its significance in shaping the evolution of the universe. This period not only marks the transition to a transparent universe, but also sets the stage for the formation of the first stars and galaxies, highlighting its crucial role in the cosmic timeline. The cosmic neutrino background is a faint, pervasive sea of neutrinos that originated from the early universe shortly after the Big Bang. These neutrinos are extremely light, electrically neutral particles that interact very weakly with ordinary matter, making them difficult to detect. They were produced in vast quantities during the first few moments of the universe, particularly during the processes that led to nucleosynthesis and the formation of light elements. While similar to the cosmic microwave background radiation, which we observe as electromagnetic waves, the cosmic neutrino background consists of neutrinos that have continued to travel through space since their creation. Detecting the cosmic neutrino background poses significant challenges due to the neutrinos' elusive nature. Their weak interactions mean that they can pass through vast amounts of material without ever being absorbed or scattered. However, researchers are developing various methods to identify and study these particles indirectly. One promising approach involves looking for the effects of cosmic neutrinos on other particles in the universe, such as those found in large-scale neutrino detectors. One key method to potentially detect the cosmic neutrino background involves using large underground detectors filled with water or other materials. When a neutrino interacts with the nuclei of these materials, it can produce charged particles, which in turn generate detectable light or sound signals. Experiments like the IceCube Neutrino Observatory, located at the South Pole, are already aiming to capture such interactions from high-energy neutrinos coming from astrophysical sources. By extending this research to lower-energy neutrinos, scientists hope to tap into the cosmic neutrino background. Additionally, scientists may explore potential signals of the cosmic neutrino background through astrophysical observations. For instance, precise measurement of the cosmic microwave background radiation and the study of large-scale structures in the universe could provide indirect evidence of the presence and characteristics of cosmic neutrinos. The interplay between dark matter, neutrinos, and the expansion of the universe is an area of active research, and further advancements in technology and observational techniques are poised to enhance our understanding of cosmic neutrinos. By shedding light on the cosmic neutrino background, researchers hope to gain insights into the physical conditions of the early universe, the nature of fundamental particles, and the dynamics of the cosmos as a whole. Detecting these elusive particles would not only deepen our understanding of the universe's history, but also potentially open doors to new physics beyond our current models. Type Ia supernovae are invaluable cosmic beacons used as standard candles for measuring distances in the universe due to their consistent peak brightness. They occur when a white dwarf star in a binary system accumulates enough mass from its companion star to reach a critical threshold known as the Chandrasekhar limit, causing a dramatic collapse and subsequent explosion. This explosion releases an immense amount of energy, resulting in a temporary luminosity that can outshine entire galaxies. What makes Type Ia supernovae particularly useful for distance measurements is their remarkable uniformity in peak luminosity. Astronomers leverage this uniformity by comparing the intrinsic brightness of Type Ia supernovae with their observed brightness from Earth. Since the inherent luminosity is well understood, any variations in brightness can be attributed to distance. By measuring how bright a supernova appears from a given distance, scientists can apply the inverse square law of light, which states that the apparent brightness of a light source decreases with the square of the distance from it. Thus, by determining the apparent brightness and knowing the intrinsic brightness, astronomers can calculate the distance to the supernova. Type Ia supernovae serve not only as distance indicators within our local universe, but also across vast cosmic scales. Their ability to be measured at great distances allows astronomers to construct a three-dimensional map of the universe, facilitating the study of nearby galaxies and those billions of light-years away. Observations of these supernovae have provided evidence for the accelerated expansion of the universe, leading to the groundbreaking discovery of dark energy. Research and advancements in technology have improved the precision of these measurements. For instance, the use of light curves graphs showing how the brightness of the supernova changes over time further refines distance estimates by allowing astronomers to standardize their methods. The combination of the uniformity of Type Ia supernovae and their reproducibility across time and distance makes them essential tools for unraveling the structure and evolution of the cosmos. The evidence supporting the accelerating expansion of the universe primarily stems from observations of distant supernova, the cosmic microwave background radiation, and large-scale structure studies. A pivotal moment in this discovery came in the late 1990s when two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, began observing Type Ia supernovae. When these teams compared the brightness of these supernovae to their redshifts, they found that distant supernovae appeared dimmer than expected. This dimming indicated that they were farther away than would be predicted by a decelerating universe. The results suggested that the universe's rate of expansion was not slowing down as previously assumed, but rather accelerating. This surprising finding led to the conception of dark energy, a mysterious force driving this accelerated expansion. Further supporting evidence comes from observations of the cosmic microwave background radiation, which provides a snapshot of the universe when it was about 370,000 years old. Detailed measurements from the Planck satellite and other experiments have revealed fluctuations in temperature and polarization patterns that align well with models predicting an accelerating universe influenced by dark energy. These measurements help to constrain cosmological parameters and confirm the presence of dark energy in the universe's energy budget. Additionally, large-scale structure surveys, such as those conducted by the Sloan Digital Sky Survey, examine the distribution and behavior of galaxies across the universe. The growth of cosmic structures over time is influenced by the rate of expansion. Observations have shown that the distribution of galaxies is consistent with predictions from a universe experiencing accelerated expansion, further corroborating the existence of dark energy. Taken together, these lines of evidence have reshaped our understanding of cosmology, revealing that the universe's expansion not only continues but also accelerates, indicating that around 70% of the universe's energy density is composed of dark energy. This reorients modern cosmology towards unraveling the nature of dark energy and its implications for the ultimate fate of the universe. Different models of dark energy are being explored to better understand this mysterious force and how it influences the cosmos. Alternative theories propose various explanations for the observed cosmic acceleration, each with unique characteristics and implications for the universe's fate. Dark energy is hypothesized to make up about 70% of the universe's total energy density and acts in opposition to gravity, driving the acceleration of cosmic expansion. Among the prominent models are the cosmological constant, dynamic scalar field theories, and modifications of general relativity. The simplest and most widely accepted model is the cosmological constant, denoted by the Greek letter lambda. This model posits that dark energy is constant throughout space and time, serving as a uniform energy density. The cosmological constant was first introduced by Albert Einstein in his equations of general relativity and was later revived to explain the accelerated expansion discovered in the late 20th century. In this framework, dark energy contributes a repulsive force that increases with the expansion of the universe, thus providing a straightforward explanation for cosmic acceleration. Dynamic scalar field theories such as quintessence propose that dark energy is not constant but varies with time and location in the universe. In these models, a scalar field evolves over cosmic time, allowing its energy density to change as the universe expands. Quintessence models can lead to different expansion histories compared to a cosmological constant and allow for a more flexible fit with observational data. These models can have interesting implications for the ultimate fate of the universe, potentially leading to scenarios such as the Big Rip or Big Freeze. Another approach involves modifications to general relativity itself, known as modified gravity theories. These models suggest that our understanding of gravity may need correction on cosmological scales. One example is the FR gravity models, where the usual Einstein-Hilbert action in general relativity is replaced with a function of the Ricci scalar r. Such modifications can produce effects similar to those attributed to dark energy while remaining consistent with local observations of gravity. While all these models aim to account for the accelerating expansion of the universe, observational data continues to guide researchers in distinguishing between them. Future astronomical surveys and advanced experiments targeting the behavior of dark energy will be critical for refining these theories, improving our understanding of dark energy's nature, and resolving the deeper questions about the fabric of our universe. Each model offers a unique perspective on cosmic expansion, enriching the scientific discourse surrounding one of the most profound mysteries in cosmology. The cosmological constant, denoted by the Greek letter lambda, plays a significant role in Einstein's field equations of general relativity by introducing a term that represents a uniform energy density filling space. Originally introduced by Albert Einstein in 1918, the cosmological constant was intended to provide a mathematical explanation for a static universe, as contemporary observations suggested that the universe was unchanging. To achieve this, Einstein added the cosmological constant to his equations, effectively counterbalancing the attractive force of gravity on cosmological scales. However, after Edwin Hubble's discovery in the late 1920s that the universe is actually expanding, Einstein famously referred to the cosmological constant as his greatest blunder, as he no longer needed it to explain a static universe. For many years, the concept was largely set aside until observations in the late 1990s revealed that the universe's expansion is accelerating. This unexpected finding reignited interest in the cosmological constant, repositioning it as a leading candidate to explain dark energy, the mysterious force driving cosmic acceleration. In the context of Einstein's field equations, the cosmological constant modifies the relationship between matter, energy, and the geometry of space-time. The standard form of the equations relates the curvature of space-time to the energy-momentum tensor, which accounts for the distribution of matter and energy. By including the cosmological constant, the equations encapsulate the influence of dark energy, allowing for a more complete understanding of the universe's dynamics. The negative pressure associated with the cosmological constant results in a repulsive gravitational effect, effectively causing the observed acceleration in the expansion of the universe. The inclusion of the cosmological constant has profound implications for cosmology. It implies that the universe will continue to expand indefinitely, leading to scenarios such as the Big Freeze, where galaxies recede from each other and stars burn out over eons. Moreover, understanding the cosmological constant's properties and behavior remains a focal point of research, as it is linked to fundamental questions about the nature of dark energy, the evolution of the universe, and the ultimate fate of all cosmic structures. Its significance in modern cosmology cannot be understated, as it continues to shape our exploration of the universe's mysteries. Astronomers measure the Hubble constant, which describes the rate at which the universe is expanding, using several methods that provide insight into the distances of celestial objects and their velocities. One prominent technique involves observing Cepheid variable stars. These stars pulsate in a regular pattern, and their brightness correlates with their pulsation period. By measuring the period and calculating their intrinsic brightness, astronomers can determine how far away these stars are in galaxies. When they compare this distance to how fast the galaxies are moving away from us, they can derive a value for the Hubble constant. Another method relies on measuring the cosmic microwave background radiation, a remnant from the Big Bang. By analyzing variations in this radiation, scientists can uncover the initial conditions of the universe and calculate the Hubble constant on a larger cosmic scale. This technique involves sophisticated models of the universe's structure and assumes the validity of the standard model of cosmology. Variations arise because different approaches can yield differing results due to their specific limitations and the assumptions involved. For example, the Cepheid variable method focuses on relatively nearby galaxies, which can be affected by local gravitational influences. Meanwhile, measurements from the cosmic microwave background encompass the entire universe, but rely heavily on theoretical models that might not be fully accurate. Additionally, uncertainties in distance measurements can lead to inconsistencies in the derived value of the Hubble constant, as small errors can greatly affect calculations. The tension between these measurements has intrigued scientists, leading to ongoing debates and research. Some theories suggest that this discrepancy hints at new physics beyond our current understanding, such as the influence of dark energy or modifications to gravity. As these methods evolve and more data becomes available, solving this could provide deeper insights into the fundamental workings of our universe. Baryon acoustic oscillations. BAOs are fluctuations in the density of baryonic matter, which consists mainly of protons and neutrons in the early universe. These oscillations were generated by sound waves propagating through the primordial plasma when the universe was still young and hot. As the universe expanded and cooled, baryons began to coalesce into structures, leaving imprints in the distribution of galaxies we observe today. Essentially, these patterns of density fluctuations act like a cosmic ruler, allowing astronomers to measure distances on a grand scale. By examining the clustering of galaxies over large areas of the sky, scientists can identify the scale at which baryon acoustic oscillations occurred. This scale corresponds to the distance between peaks in the density fluctuations, essentially measuring how far sound waves could travel before the universe cooled enough for atoms to form and light to decouple from matter. This characteristic scale serves as a marker, helping astronomers determine the expansion rate of the universe in various epochs. When comparing the observed distributions of galaxies with the expected distribution stemming from baryon acoustic oscillations, researchers can glean insights into how the expansion rate has changed over time. The information gathered from these oscillations provides a powerful method to constrain cosmological models and refine our understanding of the universe's expansion history, particularly in relation to dark energy's influence. The data derived from baryon acoustic oscillations has corroborated findings from other observational techniques, making it a critical component in the broader cosmological puzzle. Understanding these oscillations contributes dramatically to our knowledge of the universe's evolution and helps us piece together the vast tapestry of cosmic history. Dark energy is a mysterious form of energy thought to be driving the accelerated expansion of the universe. While most current models treat dark energy as a constant force, its true nature may evolve over cosmic time, presenting several intriguing possibilities. One leading hypothesis involves the concept of a cosmological constant, suggesting that dark energy remains unchanged throughout the universe's history. This consistency leads to a steady rate of expansion, as proposed in Einstein's original equations of general relativity. However, some theories speculate that dark energy could potentially undergo changes as the universe evolves. For instance, some models suggest that dark energy might dissipate or become dynamic over time. This could manifest in varying effects on the expansion rate of the universe. If dark energy were to decrease its influence, the expansion could eventually slow down, altering the fate of the universe from what we currently expect. Another fascinating possibility is that dark energy may act like a scalar field, allowing it to change in density and strength depending on cosmic conditions. This concept is reminiscent of certain theories in physics where fields can fluctuate and exert varying gravitational influences. If dark energy evolves in this manner, it could have significant ramifications for cosmic structure formation and galaxy evolution. As researchers gather more observational data, particularly from missions focused on the cosmic microwave background and large-scale structure, they remain hopeful to unlock the complexities of dark energy. Understanding whether dark energy is truly constant or if it changes over time could reshape our understanding of the universe and its ultimate fate. This ongoing investigation stands at the forefront of modern cosmology, fueling questions about the fundamental nature of reality itself. Cosmic acceleration, the phenomenon whereby the universe is expanding at an increasing rate, has profound implications for the ultimate fate of the cosmos. Current observations indicate that this accelerated expansion is driven by dark energy, a still poorly understood force that constitutes about 70% of the universe. As the universe continues to expand more rapidly, it influences how galaxies and other large structures interact over cosmic timescales. One possible fate stemming from cosmic acceleration is known as the Big Freeze. In this scenario, as galaxies move ever farther apart, the universe could grow increasingly cold and empty. Stars would exhaust their nuclear fuel and cease to shine, while galaxies would drift alone in a vast, dark expanse. With time, even the remaining black holes would evaporate through a process called Hawking radiation, leading to a stark and desolate landscape of fundamental particles scattered across an expansive universe. Alternatively, there is the concept of the Big Rip, which posits that if dark energy continues to increase in strength, it could eventually overcome all forces binding matter. In this dramatic scenario, galaxies, stars, planets, and even atomic structures would be torn apart. Such an ending would lead to a universe that becomes increasingly disrupted, concluding with a complete disintegration at a finite time in the future. Another possibility is a Big Crunch, but this scenario seems less likely in light of current data supporting cosmic acceleration. However, modifications to dark energy or other undiscovered interactions could conceivably lead to this eventual collapse. Here, the expansion could halt and reverse, culminating in a singularity similar to the one from which the universe emerged. The implications of cosmic acceleration are transformative for our understanding of the universe and its destiny. As ongoing research deepens our grasp of dark energy, these scenarios may evolve, leading to new insights into the very fabric of reality and the future of existence itself. Navigating these possibilities continues to be at the forefront of cosmological inquiry, highlighting the dynamic nature of cosmic exploration. Alternative theories, such as modified gravity, seek to explain cosmic acceleration while offering a potential solution to the dark energy conundrum. These theories suggest that rather than invoking an unknown energy that permeates space, the behavior of gravity itself may change on cosmic scales, influencing the universe's expansion. One notable framework is the modified Newtonian dynamics MOND, which posits that gravity behaves differently at very low accelerations, typically found in galactic outskirts. Another prominent approach involves the concept of scalar tensor theories, where an additional scalar field couples with gravity, modifying how it operates on large scales. These theories propose that the strength of gravitational interactions can vary across different regions of the universe. By accommodating this variability, scalar tensor models can generate an effective repulsive force that mimics cosmic acceleration without the need for dark energy. This allows for a dynamic framework where gravity adjusts to evolving cosmic conditions. Additionally, Theories like the FR gravity models extend general relativity by introducing functions that modify the Ricci scalar, which describes curvature. These modifications can lead to different gravitational responses over large distances and could account for the observed acceleration without requiring dark energy. Researchers explore these alternatives to understand how gravity might naturally evolve over cosmic time, potentially reshaping our comprehension of the universe's expansion. While these modified gravity theories present intriguing possibilities, they also face significant challenges and must account for the wealth of observational evidence supporting dark energy. As scientists continue to analyze data from supernovae, cosmic microwave background radiation, and large-scale structure formation, they seek to unravel whether these alternative explanations can robustly account for cosmic acceleration. This ongoing pursuit underscores the complexity of cosmology and the quest to reveal the underlying forces that govern the universe. Directly detecting or measuring dark energy remains one of the outstanding challenges in modern cosmology, as its nature is still largely a mystery. Several promising methods and observational strategies are being explored to enhance our understanding of this enigmatic force. One approach involves precise measurements of the cosmic microwave background radiation, which offers insights into the early universe. By analyzing the anisotropies in this ancient light, researchers can infer details about the expansion history of the universe and constraints on dark energy's properties. Another promising method is using baryon acoustic oscillations, which provide a cosmic scale reference for measuring distances. By studying the distribution of galaxies and how they cluster, scientists can map the expansion rate of the universe at different epochs. These measurements offer valuable data about dark energy's influence on cosmic expansion over time, helping to refine models and pinpoint its characteristics. Additionally, gravitational wave astronomy presents an innovative way to probe dark energy. As gravitational waves travel across the universe, their properties can reveal information about the rate of expansion and the distance to the sources. Observations from gravitational wave events like merging black holes or neutron stars could improve our understanding of dark energy through distance measurements that complement those derived from traditional methods. Finally, future large-scale surveys, such as the Vera Rubin Observatory-SS Legacy Survey of Space and Time, are set to play a crucial role in dark energy research. These surveys will produce unprecedented amounts of data on galaxy distributions, dynamics, and the geometry of the universe. By combining these observations with theoretical models, scientists aim to reveal the true nature of dark energy and its effects on cosmic evolution. Each of these methods has its strengths and challenges, and together they form a multifaceted approach to uncovering the secrets of dark energy. As technology and observational techniques advance, the quest to directly measure or detect dark energy will hopefully yield new insights that reshape our understanding of the universe. The detection of gravitational waves has fundamentally transformed our understanding of the universe by providing a novel way to observe cosmic events. Predicted by Albert Einstein a century ago, these ripples in space-time were first directly detected in 2015 by the LIGO Observatory, confirming a pivotal aspect of general relativity. This groundbreaking discovery opened a new window into the cosmos, allowing scientists to explore phenomena that have remained invisible through traditional electromagnetic observations, such as light. Gravitational waves carry crucial information about their origins, which include cataclysmic events like the merging of black holes or neutron stars. By analyzing these signals, researchers can draw conclusions about the properties of these stellar remnants, such as their masses and spins. This capability has led to a deeper understanding of the life cycles of stars, the processes leading to supernovae, and the behavior of matter under extreme conditions, bringing to light aspects of astrophysics that remained largely speculative before. Moreover, gravitational wave astronomy has introduced the concept of multi-messenger astronomy. This refers to the simultaneous observation of gravitational waves alongside electromagnetic signals, such as gamma-ray bursts or optical light from merging neutron stars. This synergy allows scientists to build a more comprehensive picture of cosmic events and enhances our understanding of the fundamental physics governing the universe. For example, The observation of the gravitational wave event associated with the merger of neutron stars resulted in the detection of kilonovae, linking heavy element formation to such cosmic collisions. Finally, by exploring the distribution of gravitational wave sources across the universe, researchers can probe the expansion history of the universe in ways that complement other methods. This research could provide new insights into dark energy and the universe's overall evolution. As gravitational wave astronomy progresses, it promises to illuminate mysteries about the universe's fundamental structure, the nature of gravity itself, and the origins and fate of cosmic entities, thereby revolutionizing our cosmic perspective. Neutrino astronomy offers a remarkable glimpse into high-energy cosmic phenomena by detecting elusive particles known as neutrinos, which are produced during some of the most violent and energetic events in the universe. Unlike other forms of radiation, such as light or X-rays, neutrinos interact very weakly with matter, allowing them to escape from their sources without being absorbed or scattered. This characteristic enables them to travel vast distances across the cosmos, providing unique information about their origins. One of the significant contributions of neutrino astronomy lies in its ability to study cosmic events like supernovae, gamma-ray bursts, and active galactic nuclei, where extreme conditions generate immense quantities of neutrinos. By capturing these particles with sophisticated detectors, scientists can glean insights into the processes occurring in these energetic environments. For instance, detecting neutrinos from a supernova could help unravel the mechanisms behind stellar explosions and contribute to our understanding of elemental processes like nucleosynthesis. Additionally, neutrinos provide a way to investigate cosmic rays, which are high-energy particles originating from outer space. When cosmic rays collide with other particles, they can produce secondary neutrinos. Detecting these neutrinos can reveal the sources of cosmic rays and provide information about their acceleration mechanisms. This is particularly important because the origins of the highest energy cosmic rays remain largely a mystery. Neutrino telescopes, such as those deployed in the Antarctic ice or under the sea, aim to observe these elusive particles with increasing sensitivity. As more data is collected, researchers expect to pinpoint neutrino sources, enhancing our understanding of high-energy astrophysical phenomena and their underlying physics. By studying neutrinos, astronomers stand to gain a more complete picture of some of the universe's most enigmatic and energetic events, ultimately shedding light on the fundamental processes that govern the cosmos. Cosmic rays, which are high-energy particles primarily composed of protons and atomic nuclei, serve as valuable probes of extreme astrophysical environments throughout the universe. These particles are generated in a variety of energetic processes associated with some of the most violent occurrences in the cosmos, such as supernovae, active galactic nuclei, and gamma-ray bursts. By studying cosmic rays, scientists can gain insights into the mechanisms driving these energetic events and the conditions in which they occur. When cosmic rays collide with atoms in Earth's atmosphere, they produce secondary particles, including muons and neutrinos, alongside a cascade of other radiation. By observing these secondary particles, researchers can reconstruct the original cosmic ray events and infer their properties, such as energy levels and elemental composition. This information serves as a key to understanding the environments where cosmic rays are accelerated to such high energies, shedding light on processes like shock waves formed in supernova remnants or interactions within the powerful jets of active galactic nuclei. The highest energy cosmic rays in particular are linked to extreme conditions that challenge our understanding of physics. By analyzing the origins and propagation of these particles, scientists are investigating potential sources like magnetars or the remnants of supernova explosions. The study of cosmic rays also raises fundamental questions about the mechanisms behind particle acceleration, including the role of magnetic fields and shock waves in their journey through the universe. Furthermore, cosmic rays can help reveal the composition of cosmic matter, providing insights into both baryonic and dark matter distributions in the universe. This can significantly enhance our understanding of galactic structures and the interplay between regular matter and dark matter in cosmic environments. Overall, Cosmic rays are essential tools for unraveling the mysteries of extreme astrophysical phenomena, offering a unique perspective on the universe's most energetic processes. Multi-messenger observations of neutron star mergers mark a groundbreaking approach to understanding some of the universe's most cataclysmic events. This methodology integrates information from different astronomical messengers, including gravitational waves, electromagnetic radiation, and neutrinos, to construct a comprehensive picture of the merger process and its aftermath. The first significant event observed in 2017 exemplified the power of this technique, as gravitational waves from the merger were detected alongside electromagnetic signals across the spectrum, including gamma rays and optical light. The significance of these combined observations lies in the wealth of information they provide about the physics of neutron star mergers. Gravitational waves deliver precise data about the dynamical processes involved in the merger, including the masses and spins of the component stars. These measurements allow researchers to test and refine their models of neutron star behavior and strong field gravity, offering insights into fundamental questions of astrophysics and general relativity. Electromagnetic signals, on the other hand, reveal the aftermath of the merger. When neutron stars collide, they can eject material at high velocities, leading to the production of kilonovae, brilliant explosions that emit light across various wavelengths. The study of these light curves informs scientists about the nucleosynthesis processes occurring during the merger, particularly the creation of heavy elements such as gold and platinum. This not only enhances our understanding of how such elements are formed, but also offers clues about the origins of the observable universe's elemental composition. Furthermore, the combination of gravitational wave and electromagnetic data allows for a more accurate measurement of cosmic distances and the expansion rate of the universe. By linking the observed properties of neutron star mergers with their gravitational wave signals, astronomers can calibrate cosmic distance scales with unprecedented precision. This cross-disciplinary approach highlights the interconnectedness of different astronomical phenomena and heralds a new era in astrophysical research, paving the way for future discoveries about the intricate workings of our universe. Gamma-ray bursts are among the most energetic and luminous events in the universe, serving as powerful beacons that illuminate extreme cosmic phenomena. These bursts, which can release as much energy in a few seconds as the sun will emit over its entire lifetime, originate from cataclysmic processes, including the collapse of massive stars or the merging of neutron stars. Their intense emissions are detectable across vast distances, providing insight into the most violent occurrences throughout the cosmos. When a gamma-ray burst occurs, it releases intense beams of gamma rays that can be observed across the electromagnetic spectrum. These bursts often trigger alerts in astronomical observatories, leading to rapid follow-up observations. The swift detection allows astronomers to study their afterglows, which emit light in radio, optical, and X-ray wavelengths, enabling a comprehensive analysis of the event and its environmental context. This multi-wavelength approach helps researchers unravel the mechanisms driving these extreme explosions. Gamma-ray bursts also offer a unique opportunity to study the early universe, as their high luminosity allows them to be observed from great distances. This provides information about the conditions in the early universe and the formation of the first stars and galaxies. Additionally, the study of gamma-ray bursts contributes to our understanding of the cosmic star formation history, the interstellar medium, and the processes that lead to the synthesis of heavy elements. Gamma-ray bursts GRBs provide a unique opportunity to probe the conditions of their host environments. The immense energy released during these bursts can illuminate the surrounding matter and indicate star formation rates in distant galaxies. By studying the light curves and spectral features of these bursts, scientists can extract information regarding the materials in their surroundings, providing clues about the evolution of galaxies and the processes that lead to the formation of such massive stars. Additionally, the immense reach of GRBs allows them to serve as cosmic distance markers. By analyzing their properties and distances, these bursts can help astronomers refine their understanding of the universe's expansion and the rate of cosmic evolution. Their extreme nature and the variety of circumstances that give rise to them make GRBs crucial for exploring the extremes of astrophysics and enriching our understanding of the universe's evolution. Gravitational microlensing is a powerful astronomical technique that provides significant insights into the presence and properties of dark objects in the universe, such as black holes, neutron stars, and potentially dark matter. The fundamental principle behind microlensing is based on Einstein's theory of general relativity, which posits that massive objects like stars or galaxies can bend the light coming from more distant objects when they pass in front of them. This bending of light can create temporary increases in brightness, allowing for the measurement of the gravitational effects of these dark objects. One of the primary applications of gravitational microlensing is the detection of dark matter in the form of compact objects that do not emit light. While traditional methods rely on observing light from stars and galaxies, microlensing can identify objects like primordial black holes or other unseen stellar remnants by measuring how they affect the light from background stars. For example, when a dark object passes in front of a more distant star, it magnifies the light without altering the background star's intrinsic characteristics, creating a detectable signature in brightness. Moreover, microlensing surveys have the potential to reveal the population and distribution of these dark objects, providing critical data to illuminate the nature of dark matter and its role within the broader cosmic structure. A successful microlensing event can yield valuable parameters such as the mass of the lensing object and its distance, contributing to our understanding of how matter, both visible and dark, interacts and forms structures in the universe. In addition, the analysis of statistical trends from multiple microlensing events can help constrain theories regarding dark matter and suggest whether it consists of relatively large compact objects or something more exotic. As researchers continue to gather data through various surveys, gravitational microlensing remains a vital tool for exploring unseen components of the universe, enhancing our understanding of its composition and the distribution of dark matter. Astronomers use a technique called multi-wavelength astronomy to combine observations across the electromagnetic spectrum, investigating cosmic phenomena with greater depth and detail. By analyzing light from radio waves, infrared, optical, ultraviolet, X-rays, and gamma rays, scientists can gather a comprehensive view of celestial objects and processes that standard observations in just one wavelength might miss. Each wavelength reveals distinct characteristics of astronomical phenomena, allowing for a richer understanding of the universe. For instance, radio waves can penetrate dense regions of dust, providing information about star formation in molecular clouds that optical observations might obscure. Infrared observations help trace cooler objects such as brown dwarfs and distant galaxies, while optical data can reveal detailed structural features in stars and galaxies. Ultraviolet light often highlights hot young stars, giving insights into stellar populations and their evolutionary stages. Meanwhile, X-rays and gamma rays can detect the high-energy processes surrounding black holes, neutron stars, and supernova remnants, unveiling phenomena that occur in extreme conditions. Combining these various datasets allows astronomers to create a more complete picture of cosmic events. For example, when studying a supernova, optical light can show the explosion, while X-ray observations reveal the immediate aftermath and interactions of shock waves with surrounding material. By interlinking information from these observations, scientists can build models that explain the life cycles of stars, the formation of galaxies, and the behavior of matter under intense gravitational fields. Advancements in technology and the development of specialized telescopes have facilitated the collection of multi-wavelength data. Observatories like the Hubble Space Telescope and the upcoming James Webb Space Telescope specialize in capturing different parts of the spectrum, enabling collaborations that enhance understanding across disciplines. This comprehensive approach is vital for unraveling the complexity of the universe and differentiating between various astrophysical processes, ultimately enriching our understanding of celestial phenomena. Fast radio bursts FRBs are intense, brief pulses of radio emission from distant galaxies, lasting only milliseconds but releasing immense amounts of energy. Their discovery has sparked excitement in the astrophysics community due to their potential as cosmic probes for studying a wide range of phenomena in the universe. The most compelling aspect of FRBs lies in their ability to serve as beacons that offer unique information about the intergalactic medium and the environments they traverse on their journey to Earth. One of the primary uses of FRBs as cosmic probes is in the study of cosmic baryons, the ordinary matter that makes up stars and galaxies. Each FRB emits light that interacts with the material in space, leading to observable effects such as dispersion, where the signal's higher frequencies arrive before lower frequencies. By analyzing the dispersion measure, astronomers can gain insights into the density of electrons in the interstellar and intergalactic medium, helping to map the distribution of baryonic matter throughout the universe. Additionally, FRBs may reveal new information about the large-scale structure of the cosmos. Their extreme distances mean they can probe regions of space that are otherwise difficult to study. They can illuminate the effects of dark matter and the distribution of matter on cosmic scales, providing valuable data about the evolution of cosmic structure over time. Observations of FRBs from various locations in the universe could also help test theories related to the expansion of the universe and the nature of dark energy. Moreover, the unique characteristics of FRBs can lead to inquiries about the environments where they originate. The extremes of the host galaxies, including magnetic fields and dense matter regions, may influence the properties of the bursts. Understanding the conditions surrounding FRBs could reveal important clues about their progenitors, potentially linking them to phenomena like magnetars or other exotic stellar objects. As detection technology improves and more FRBs are observed, the potential of using these enigmatic signals as cosmic probes will only continue to expand. By studying their frequencies, dispersion, and temporal characteristics, astronomers stand to unlock critical insights into the fundamental properties of the universe, bridging gaps between astrophysical phenomena and enhancing our understanding of cosmic evolution. Future gravitational wave observatories hold the promise of greatly expanding our understanding of the universe by enhancing the detection capabilities and frequency at which we can observe gravitational waves from a diverse array of cosmic events. With ongoing advancements in technology and new innovative designs, these observatories aim to capture signals that are currently beyond our reach, enabling astronomers to probe the universe in unprecedented ways. One key aspect of future gravitational wave observatories is their ability to detect events occurring at different distances and masses. While current observatories like LIGO and Virgo have successfully identified mergers of stellar black holes and neutron stars, upcoming facilities such as the Einstein Telescope in Europe and the Cosmic Explorer in the United States will be sensitive enough to detect signals from a wider range of astrophysical phenomena. These might include the mergers of supermassive black holes at the centers of galaxies or other exotic events, offering insights into their formation and growth over cosmic time. Additionally, increasing the sensitivity of these observatories will allow for shorter and fainter gravitational wave signals to be detected. This capability will enable scientists to study less common events and provide information about a broader set of binary systems. Such observations are crucial for exploring the population characteristics of black holes and neutron stars, contributing to our understanding of stellar evolution and the life cycles of massive stars. Future observatories also aim to facilitate multi-messenger astronomy, a practice that combines gravitational wave data with information from electromagnetic signals, neutrinos, and other forms of radiation. By understanding the same event through multiple lenses, scientists can build a more comprehensive picture of the underlying processes at play. For example, associating gravitational waves from a neutron star merger with electromagnetic counterparts will provide insights into nucleosynthesis and the formation of heavy elements, providing crucial connections between astrophysics and cosmology. Overall, the next generation of gravitational wave observatories promises to revolutionize our understanding of the universe, enhancing our ability to probe its most extreme environments and phenomena. Through expanded detection capabilities and the integration of multi-messenger data, These observatories will deepen our foundational knowledge of fundamental physics, stellar evolution, and the intricate workings of the cosmos. Multi-messenger astronomy, which combines information from various types of astronomical signals, such as gravitational waves, electromagnetic radiation, and neutrinos, holds significant potential for uncovering aspects of dark matter, one of the most perplexing components of the universe. By employing different messengers, researchers can piece together a more comprehensive understanding of dark matter's properties, distribution, and interactions. When it comes to identifying dark matter, gravitational waves can provide critical insights. Observations of events like neutron star mergers may reveal the presence of dark matter through its gravitational effects on surrounding matter. For instance, if dark matter interacts weakly with baryonic matter, its influence could alter the dynamics of stars or gas near these merger events. Understanding such interactions could illuminate the nature of dark matter and help differentiate between various theoretical models that attempt to explain it. In addition, cosmic rays, high-energy particles that can be categorized through multi-messenger observations, might provide indirect evidence of dark matter. Certain theories propose that dark matter could annihilate or decay into standard model particles, producing detectable cosmic rays as byproducts. By analyzing the energy spectrum and composition of cosmic rays, astronomers may discern signatures of dark matter interactions, thereby generating new information about its characteristics and abundance throughout the universe. Neutrino observations also play a crucial role in exploring dark matter. Certain models, like those involving heavy dark matter candidates known as weakly interacting massive particles WIMPs, suggest that such particles could produce high-energy neutrinos when they annihilate in regions of dense dark matter, such as the centers of galaxies. By detecting these high-energy neutrinos, astronomers can infer properties about dark matter and its distribution in the universe. Ultimately, multi-messenger astronomy allows for a more nuanced approach to understanding dark matter, offering pathways to test predictions of various models and theories. By linking observations across multiple channels, scientists can refine their understanding of dark matter's role in cosmic structure formation and evolution, paving the way for discoveries that could significantly enhance our understanding of the fundamental nature of the universe. The observable universe is defined as the region of the universe from which light has had sufficient time to reach us since the beginning of cosmic time, approximately 8 billion years ago. This definition inherently links the observable universe to the finite speed of light and the age of the universe itself. Essentially, it is the largest volume of space that we can currently study or observe, limited by the limitations of light travel time and the expansion of space. To measure the size of the observable universe, astronomers utilize the concept of the cosmic light horizon, which represents the maximum distance light has traveled since the dawn of time, accounting for the universe's expansion. This horizon provides a boundary beyond which we cannot see, as light from objects that exist beyond this limit has not been able to reach us due to the finite speed of light. The observable universe is estimated to have a diameter of about 91 billion light-years, which takes into account the expansion of space itself over time. Determining the observable universe's size involves calculating distances to various celestial objects. Standard candles like supernovae or Cepheid variable stars are commonly used as reference points for measuring distances. By plotting these distances in relation to their redshifts, the effects of the universe's expansion on the wavelengths of light, scientists can map out how far we can observe for different regions of space. Additionally, modern cosmological models and observational data from missions like the Wilkinson Microwave Anisotropy Probe and the Planck Satellite have refined our understanding of the observable universe. By studying the cosmic microwave background radiation and the large-scale structure of the universe, scientists gain evidence that informs their calculations, offering a clearer picture of the limits of our observable universe and its overall dimensions. Ultimately, the concept of the observable universe highlights the fascinating interplay between time, distance, and the expansion of space, presenting a challenging yet crucial framework for understanding the cosmos and our place within it. The limit of our cosmic horizon is determined primarily by the finite speed of light, combined with the age of the universe and the expansion of space itself. Light travels at a constant speed of approximately 300,000 kilometers per second, which means that the maximum distance we can observe is dictated by how long light has had to travel since the dawn of the universe. Given that the universe is approximately 13.8 billion years old, we can observe objects whose light has taken that amount of time to reach us, leading to the concept of the observable universe. However, the expanding nature of the universe complicates the straightforward relationship between distance and light travel time. As the universe expands, the distance between objects increases over time, causing light emitted from very distant sources to be redshifted. This redshift affects how we calculate distances because it reflects the stretching of space, which means that while the light may have taken billions of years to reach us, the actual physical distance to these objects has increased during that time. Therefore, when we speak of the observable universe having a diameter of about 91 billion light-years, we account for this expansion. Additionally, the nature of the cosmic microwave background radiation plays a role in determining the limit of our cosmic horizon. The background radiation is the remnant light from the Big Bang that fills the universe and provides a snapshot of the early universe. Understanding this radiation informs our models of cosmic expansion, allowing us to refine our estimates of the limits of our observable universe. Moreover, gravitational effects and the geometry of space-time, influenced by general relativity, also contribute to our understanding of cosmic horizons. The structure of the universe, including dark matter and dark energy, impacts how space itself expands and how light propagates through it. As scientists study these factors using various observational techniques and theoretical models, they continue to deepen their understanding of the cosmic horizon and its implications for the universe. The concept of light travel time fundamentally shapes our understanding of the distant universe by providing a temporal and spatial framework through which we interpret astronomical observations. When we observe celestial objects, we are essentially looking back in time because the light we see has taken a finite amount of time to reach us. This means that the more distant an object is, the older the light we are receiving, allowing astronomers to study the universe's history and evolution. For instance, when we gaze at a galaxy that is 12 billion light-years away, we are seeing the light emitted from that galaxy 12 billion years ago. This offers a window into the past, revealing how galaxies formed and evolved in their early stages. As a result, light travel time helps establish a timeline of the universe, allowing scientists to piece together events like the formation of stars, the evolution of galaxies, and the behavior of matter under different cosmic conditions. Furthermore, light travel time influences our understanding of the universe's expansion. As light from distant objects reaches us, we observe that its wavelengths have been stretched due to the expanding fabric of space, resulting in redshift. This phenomenon informs our insights into the rate of expansion of the universe, contributing to measurements of the Hubble constant and providing critical data for cosmological models. Additionally, light travel time frames the limitations of our observations. While we see objects that are billions of light-years away, it is important to remember that there is a cosmic horizon beyond which we cannot see. This horizon is dictated by the age of the universe, as light from objects beyond this limit has not had enough time to reach us. As a result, our understanding of the universe is inherently constrained by light travel time, shaping both the information we gather and the interpretation of cosmological phenomena. Ultimately, the concept of light travel time remains a foundational aspect of how we explore and understand the cosmos, allowing us to connect present observations with the rich history of the universe. Through this lens, astronomers can unravel the complexities of cosmic evolution and the underlying mechanisms that govern its structure and dynamics. Cosmic expansion has a profound impact on our ability to observe distant objects, shaping both the characteristics of the light we receive and the distribution of those objects across the universe. This expansion is a fundamental aspect of the universe described by Hubble's law, which states that galaxies are moving away from us and that their velocity is proportional to their distance. As the universe expands, the distances between galaxies increase over time, which affects the light emitted from these distant sources. One of the primary effects of cosmic expansion is redshift. As light from distant objects travels through expanding space, its wavelengths become stretched, causing the light to shift toward the red end of the spectrum. In space, there is no up or down. There is only infinity and boundless possibilities. Neil deGrasse Tyson. Astronomy and cosmology stand as two of the most exciting and rapidly evolving fields of science, unlocking the mysteries of the universe. Modern advancements in observational technology, modeling, and data analysis are enabling scientists to explore the cosmos on unprecedented scales and levels of detail. New methods such as multi-messenger astronomy and artificial intelligence are providing a more comprehensive understanding of cosmic processes, from the birth of stars to the collisions of black holes and neutron stars. One of the most intriguing topics is the study of dark matter and dark energy, which make up a significant portion of the universe, yet remain invisible and mysterious. Advanced detection methods for dark matter and the integration of data from various types of astronomical signals promise to reveal the fundamental properties of these components and their roles in the evolution of cosmic structures. Additionally, technologies such as interstellar probes and space-based telescopes are expanding our horizons, allowing for direct exploration of nearby star systems and their planets, as well as the search for signs of extraterrestrial civilizations. These investigations not only deepen our understanding of the universe, but also prompt us to rethink our place in the cosmic landscape. This introduction to contemporary and future cosmic research illustrates how cutting-edge technologies and data analysis methods are helping humanity get closer to unraveling the deepest mysteries of the universe, pushing the boundaries of science and opening new horizons for exploration. Earth's position in the solar system is often referred to as being in the Goldilocks zone, a region around the sun where conditions are just right for sustaining life. This zone is neither too hot nor too cold, allowing water to exist in liquid form, which is crucial for all known life. As the only planet we know of with stable bodies of liquid water, Earth serves as an ideal habitat for organisms ranging from the simplest bacteria to complex multicellular life forms. Additionally, Earth's distance from the Sun helps regulate its climate. Our planet experiences a relatively stable climate because of the energy it receives from the Sun, allowing it to maintain an atmosphere rich in gases necessary for life. The presence of a breathable atmosphere composed primarily of nitrogen and oxygen protects living beings from harmful solar radiation and helps maintain a temperature range conducive to survival. Earth's structure also contributes to its habitability. It has a strong magnetic field generated by its molten iron core, which shields the planet from cosmic radiation and solar winds. This protection helps maintain our atmosphere and contributes to stable climatic conditions. Furthermore, the presence of diverse ecosystems fosters biological diversity, which is essential for resilience and adaptability in facing environmental changes. Interestingly, Earth's orbital characteristics, such as its axial tilt, contribute to the changing seasons, promoting biodiversity by creating different habitats throughout the year. This combination of factors, distance from the Sun, presence of water, a protective atmosphere, and a magnetic field, creates a uniquely balanced environment that has allowed life to flourish over billions of years. If Earth's orbit were to shift slightly closer to the Sun, even by a small fraction, the consequences for life as we know it could be significant. A decrease in distance would increase solar radiation reaching our planet, leading to higher global temperatures. This warming could accelerate climate change, melt polar ice caps at a more rapid pace, and cause sea levels to rise dramatically. A warmer Earth would also disrupt ecosystems, with many species struggling to adapt to the rapid changes in their habitats. On the other hand, if Earth were to drift slightly farther from the Sun, it could plunge the planet into a cooler state. Lower temperatures would likely result in extended periods of winter, potentially locking large areas in perpetual ice. This scenario could greatly affect agricultural practices, limiting the availability of food resources and leading to population declines. Additionally, a colder Earth would see habitats shrink, making it difficult for many species to survive, thereby increasing the risk of extinction for countless organisms. Both scenarios highlight the delicate balance that sustains life on our planet. Earth's current distance from the Sun has been finely tuned over millions of years, allowing for the stable conditions necessary for diverse biological life. Changes in this balance could trigger complex feedback loops within the climate system, leading to unpredictably harsh consequences that would extend beyond immediate temperature changes, impacting weather patterns, ocean currents, and other environmental factors. Intriguingly, Earth's orbital characteristics are not static. They are influenced by gravitational interactions with other celestial bodies. This means that even subtle changes can have far-reaching implications for our climate and ecosystems. Thus, understanding Earth's position in relation to the Sun is not just an academic exercise, but rather a vital consideration for grasping our planet's future and the survival of life within it. The gravitational forces exerted by other planets in our solar system play a significant role in influencing Earth's orbit and climate over long periods. This interconnectedness results from the gravitational interactions among the solar system's bodies, particularly the larger planets like Jupiter and Saturn. Their immense masses can cause slight variations in Earth's orbit known as perturbations. These changes can impact the shape of Earth's orbit, its axial tilt, and even the timing of the seasons, albeit very gradually. One of the most compelling phenomena influenced by these planetary interactions is the Milankovitch cycles. These cycles result from the combined gravitational effects of the Sun and the other planets, leading to variations in Earth's tilt and eccentricity of orbit over tens of thousands to hundreds of thousands of years. These shifts contribute to long-term climate changes, including the onset of ice ages and warm periods throughout Earth's history. Jupiter, in particular, acts as a gravitational shield for the inner planets. Its substantial mass allows it to capture or deflect comets and asteroids that could otherwise threaten Earth. This protective role plays a crucial part in preserving Earth from potential cataclysmic impacts, thus contributing to a stable climate over geological timescales. On the flip side, shifts in the gravitational dynamics could hypothetically lead to increased risks from wandering